Hi guys, it's Sabrina here. I'm going to be running through the Orgo 2 Exam 2 2019 for Dr. Bean. I'm so sorry that we're not going to be able to have the Orgo reviews in person, but hopefully this will be of help for you guys and you guys are staying safe and healthy. We're going to run through the entire thing from start to finish, of course beginning with nomenclature. So let's get to it. So starting with nomenclature, we have introduced a couple new functional groups, and we've also introduced benzene rings. Okay, so I found this really cool table in the book. It doesn't say the page necessarily, but it's towards the end if you're looking for it. And I also came and I copy and pasted it here into a blank page so you can see it. And where we have gotten to thus far, I'm going to mark for you guys where we've gotten to. Basically right here. So we've added, when we were in Orgo 1, we stopped at the alcohols being the highest priority group. That's what's really nice about this table, is that it orders it in the direction of highest priority at the top, all the way down to your ethers and your halides at the very bottom. And in Orgo 1 and for the last exam of Orgo 2, we got up to alcohols as our highest priority group. You'll notice this trend of as you go up the table, the higher the oxidation, the higher the oxidation state, the higher priority. So that's why your carboxylic acid is going to be at the very top of the chain. And then what's our highest priority thus far is going to be our new groups, our aldehydes, as well as our ketones. And it kind of describes, if it's the parent, how you would change the name, and if it's a substituent, how you would name these functional groups. And it goes all the way down to the halides, okay? So that's what we're going to be looking for. In addition to that, you're going to want to know your benzene rings, the benzene derivatives. There's some names that are commonly used. You're going to want to have those memorized. I think there's about 8 of them, but go and check. There's a particular page in the book for those, okay? Now let's get started with the first question. So of course, as always, we want to identify what is our highest priority group in this molecule. All right, so we have an aldehyde, we have a hydroxy, an alcohol. So what's going to be of higher priority? So your answer should be the aldehyde, right? So I'm going to include that in my parent and pick the longest chain possible that I can, okay? So if we go this way, we're going to get 1, 2, 3, 4, 5, and 6 carbons, okay? Versus the other way would be 5. So this is going to be our parent chain that I highlighted. So I'm going to write parent over here, kind of as we always do. And of course, the way that I numbered it, I did that on purpose. Why would I number it that way as opposed to left to right? So the reason why I would do that is in order to put my highest priority group on the lowest number possible, okay? So I kind of ignored the fact that I have that substituent here, as well as the fact that I have the hydroxy group because my aldehyde is of highest priority, all right? So I want to put that on the number 1 carbon. Now we established that there's six carbons in our parent chain. So what's our prefix going to be? It's going to be hex, right? And now we're going to have to indicate that our aldehyde is our parent. So in order to do that, you keep it as it would normally be, but you change the ending to al, just like in the name aldehyde, right? That's where it's coming from. So you have a hexanal. And with the aldehydes, if it's a part of your parent, do we have to put the number 1 in front? So your answer should be no, because it's implied that an aldehyde is at the end of the molecule, right? It's at the end of the parent chain. So for that reason, we don't have to put 1 hexanol. We can just write hexanol and we're good to go. All right? And now let's account for our substituents, okay? So let's write the word sub over here and figure out what we have coming off. So at our number 4 carbon, we have this group, the benzene ring. So let's indicate that it's coming from 4, and it has this CH2, this methylene right in the middle. So it's not directly attached to the parent, the benzene ring. It's not directly attached as such. So when you're trying to name this as a substituent, you would call it benzyl. Right? If you're trying to name what I put on the very left, you would actually call this, what do you guys think? Phenol, okay? Versus benzyl is what we have in our particular molecule. Now, what other substituent do we have? We have hydroxy. And our hydroxy is coming from which carbon? 6. So be careful to write hydroxyl, right, with an L at the end. When the alcohol is a substituent, which we haven't really seen before, but once it's a substituent, you make it hydroxy, no L at the end. Now, in terms of writing this entire molecule out in our box, how are we going to decide the order at which we write it out? So it's going to be alphabetical order. So, of course, the B comes first. So we're going to put 4 benzyl dash 6 dash hydroxy. And then are we going to put a space in between hydroxy and hexanol? Nope. No space at all, okay? It's continuous. You want to be really careful with the spaces and stuff, because you'll see later on in Orgo 2, there will be times where you have to include spaces, and that is for points, okay? So that's how we answer the first question. You guys can type up if you have any questions about the first problem, okay? Now let's move forward to the next one. So of course, our first step is gonna be identifying what is our highest priority group, and from that, picking our parent, right? So what do you guys think is our highest priority group? So our highest priority group in this molecule is going to be the ketone. It's going to be this right here, right? So once we have established that, we need to make the parent about that ketone. So it's a part of the ring, right? So for that reason, we're going to make this the parent chain. Let me include the ketone, right? And whenever you make the ketone the parent, and that ketone is a part of a ring, you arbitrarily pick the numbering, right? And you have to pick the numbering so that if the ketone is your parent, then the ketone automatically, right, by default, that carbonyl must be located at your number 1 carbon. I need to plug in my iPad. 1 second. Okay. So that ketone needs to be at your number 1 carbon by default. So we're not going to have to indicate a 1 for that. But let's go ahead and start writing our parent out. So how many carbons do we have? 6. So what is our prefix going to be? Hex. And it's a part of a ring, remember? So in the front, we're going to put cyclo. Right? And then for the 6 carbons, we're going to put hex. Right? And then within this parent, we also have a double bond, right? So we're going to have to account for that eventually, okay? So right now we haven't numbered it. So let's actually go back and try to figure out if we can number our ring. So are we going to number our ring clockwise, or are we going to number it counterclockwise? Right, so we have these two options of how we want to go about the ring, okay? So let's say that we're going to go clockwise, right? So if we were to go clockwise, then our numbering would be 1, double bond starts at 2. We would get 1, 2, 6. If we were to go counterclockwise, what would we get? 1. Here, let me put it in a different color, just to clearly distinguish between the two. So we would get 1, 2, so we would get 1, 2, 5. Do you guys see that? So which route are we going to take? The one of the lowest number, okay? Right? So once you have, basically the point is that once you have established, your ketone is your highest priority group, then if we're trying to figure out the numbering from that, right, you have to make the decision based upon getting those substituents on the lowest number possible. You see what I mean? It is not based upon their alphabetical order. Okay, the only time you would resort to alphabetical order is if both ways you got the same numbering. If you got 1, 2, 5 and 1, 2, 5. Here, we can already establish this is the lowest number. We're going to number it the purple route, okay? So let's erase all the red. So 1, 2, 3, 4, 5, 6. Okay, so that's how we make that decision, okay? Consider the alkene and that other substituent, they are equal in terms, you kind of close your eyes and look at them all equally, okay? That is after you've already decided that your ketone is the parent. All right, so we got cyclohex, and then where is our double bond located? Which number? Located at 5, right? Because we're going to have to write and indicate that there's a double bond in here with the hexane, right? Instead of ane. And then we have to indicate that it's coming off of our 5th carbon in the molecule. So then after that, we have to account for the ketone, right? So cyclohexanone for ketone. Okay, so that's going to be our parent. I'm going to put the 5 in the front just because I think it looks prettier. But let's now move forward to our substituents and see what we have here. So the only thing I see is that group coming off over there, right? And that is a complex substituent because you also have this bromine coming off, okay? So what are we going to call that? Well, first, let's number, starting, you always start from the carbon that is coming directly, that is directly attached to your parent. So that would be our number 1. And then we number it in such a way to give us bromine on the lowest number, right? Same rules apply. So we're going to put that as 3 bromo. And then our pseudo parent for the complex substituent is phenol. Right? It's not benzyl. We're going to put these within parentheses because it's a complex substituent, and then we have to indicate where is that coming off of our original parent. Where do you guys say? 2. Right? Now that we've accounted for everything, we can write this in the box. And write our full name out. And I'm going to look at the key after I write this out, just to see if there's any tips. Make sure everything looks good alongside Dr. Bean's key, okay? So no worries about that. So let me check it. So we're good to go. The only thing is that if you prefer to put meta, right, you could also do that, okay? basically in replacement of that. So you wouldn't write the word meta, you would write M dash, okay? So that's indicating that to that, okay? That's up to you. You can only use that naming when you have two substituents on the ring, okay? So be very careful about that, okay? That's the relationship between only two substituents. Now let's move forward to our third one and see what we have going on here. So what's our highest priority group? You guys should be saying carboxylic acid. And I see this carboxylic acid here. Right? This looks like this. If you draw the entire thing out. So of course that is very oxidized. So that is our highest priority group. We are gonna make our parent include that highest priority group. So I'm gonna write parent there. And now this is kind of what I was talking about earlier, where you're gonna wanna know the names for these benzene derivatives, just because they're so common, and she can sometimes even write out the name and then ask you to draw the structure. So you wanna be able to identify them and recall them. So for this one in particular, what is it gonna be called? Benzoic acid. Okay, and I can give some examples of those. So the one that we have up there is benzoic acid. Let's say it was replaced with an aldehyde. For example, let's say we had this. That's going to be benzaldehyde. Okay, let's say we had a methoxy group on there instead. That's going to be called anisole. Let's say that was replaced with an amino group. That's going to be aniline. So these are the common ones. And then let me see if I can think of one more. Okay, so let's say we had a benzene with just a CH3, right? A methylbenzene, basically. You could also call it toluene, like that. Okay, and then of course the benzoic acid, we have that one up there. But look in the book for any others. Now that we established that that is benzoic acid, we can move forward and think about our subs and also the numbering of this ring, which I should do first actually. So what's gonna be our number one? Well, it has to be in regards to the parent, right? So our parent is the carboxylic acid, so that's gonna be our number one right there. And then we go all the way around the ring in such a manner that we put that substituent on the lowest possible number we can. So we're gonna do it as such, right? And that is our numbering. Let's move to the naming of that substituent. So this is gonna be also a complex name, okay? So we will start with numbering that, and I'm gonna number it clockwise in order to get me that substituent on the lowest number, aka this right here. Because this, remember, this is like a pseudo parent to the substituent. So whenever you have like an aldehyde or a ketone, it's not a part of the original parent, right? When I say original parent, what I mean is this yellow, the highlighted and yellow over here. Okay, this is a substituent, and now that it's considered a substituent, we consider this to be a substituent to that. So whenever you have that, basically a ketone as a substituent, we are gonna name it using the word oxo. And if we had an aldehyde, for example, we are gonna name it using the word formyl. Okay, so here we have the ketone. So basically, when we ask ourselves, we have a ring, how many carbons do we have? So cyclo, right? for the ring. And then we have 6 carbons, so cyclohexyl, right? And then within this cyclohexyl, we have a oxo group at 2. So we have 2 oxocyclohexyl, and then this is the entire group. And then we have to indicate where is that entire thing coming off of our original parent. And it's coming off of the number 3 carbon. So we're going to put 3 right there. And then, of course, this is the entire thing, which we're going to have to write in our box now that we're done. Okay, an important question. Is there going to be a space between benzoic and the cyclohexyl? Nope, it just continues on, but there is a space between benzoic and the word acid. Okay, let me check her key. Perfect. So if you also wanted to put here the letter M, indicating meta, indicating that in between this group and this group, right, that's meta to the carboxylic acid, could totally do that, you know, in replacement of the 3. Okay? So that is nomenclature. Let me zoom out. There. All right, so now you guys, we're going to continue on with the fact section. And now the exam, there's a likely chance that the exam for the upcoming Friday is not going to happen. However, I think that this is a very important section here, the fact section, the reaction section, as well as the synthesis, spectroscopy. I mean, they're all really important, and this is very cumulative. So this first question up here at the top, they like to test this on the ACS exam. You know, I've seen it when I was practicing for that, when I was in the class, as well as on my actual ACS exam when I took the class for the final. So I would pay attention to the Huckel's rule. It's very important. All right. So let's read what it says. It says, label the molecules below as aromatic, anti-aromatic, or non-aromatic, and please assume that all of these are planar. Okay, so they're telling us that these are planar, and that will make a difference later on when we're trying to make decisions. Let's go back up here and write some notes. So it gave us 3 different classifications for molecules. Okay, and these are going to differ based upon their energy levels, aka how stable they are. So let's start, for example, with aromatic. So if this is our energy diagram right here, aromatic compounds, they have this extraordinary stability to them. So that means they're going to be lowest in energy in comparison to the others, right? They are extra stable. That is great. If a compound is aromatic, that is great. There is delocalization of the pi electrons about the system that is allowing for that to be more stable. Now let's compare to the second option, which is anti-aromatic. So anti-aromatic is going to be highest in energy level, the least stable out of these 3. And then right in the middle, your little compromise, you could call it, is going to be non-aromatic. So we'll denote that as Na. Okay. So that's in terms of energy. And what we're going to want to do when solving these questions here. So like, let's look at the first one, for example. There's something called the Huckel's rule, and we'll go over that as well. So what you want to do is try to count the number of pi electrons in the system. And you can focus on those that are part of double bonds, for example, because those are going to be your easiest ones. They're always going to be acting as pi electrons. So let's start off with that. So for this first one on the left, 1, 2, 3, 4. So far we found 4 pi electrons, right? Then let's look to the carbon on the right over here, right? So what is attached to this carbon that we're not showing in order for this to be a carbanion with a minus charge? There must be a hydrogen there, right? If you calculate the formal charge for that, you would get it to be 1, 2, 3, 4, 5, and then 4 minus 5 gives you minus 1. So that's a carbanion, and you have this hydrogen here. So this is where I tell people that it can help you to know what the orbitals look like, okay? So let's say we want to figure out what is the hybridization of that carbon. What is the hybridization? So you guys should say the hybridization is sp2. And the reason why I'm saying sp2, despite the fact that we see 1, 2, 3, 4, the lone pair counts as a fourth group, so you would think, oh, this is going to be sp3, right? However, there can be some resonance drawn here. This can resonate inwards, push this, and so on, right? So whenever there's resonance and we're trying to figure out the hybridization of a carbon atom like that, we're going to take the lowest possible hybridization and consider that to be the hybridization of that carbon. Okay, so this is an sp2 hybridized carbon, right? And if we consider that lone pair versus the hydrogen, right, we want to consider what type of orbital is the lone pair, or the lone pair, what type of orbital is that in? Okay, so remember, when we have an sp2 hybridized atom, we have three sp2 hybridized orbitals, right? And in addition to that, we're going to have an unhybridized p orbital. Right? So imagine you have an S, and you have a P, and a P, and these guys morph together. They make a hybrid of an sp2 orbital. And then, of course, you still have that remaining P, because there's typically, that's your S orbital, and then you typically have a P, P, and P, right? That's the maximum. So if these formed a hybrid to make the sp2s that we see below, then what about that final p orbital, right? So that final p orbital stays unhybridized, stays on its own, and that's where you get that unhybridized p that I am talking about down here. Okay, and in terms of the sp2 hybrids, what these orbitals look like, we're going to say they kind of look like this. I'm not going to show the small lobe on the back side because there's no point. But we would also have the sp2 hybridized orbital to the hydrogen, right? So we have one to the carbon, one to the carbon, one to the hydrogen. And then we have this lone pair, and the lone pair is going to be present. Let me draw in blue, for example. The unhybridized P make these dumbbell shapes like that above and below the plane of those sp2 hybridized orbitals, okay? So the lone pair is going to be present in that, okay? And then it's going to be traveling throughout this pi system, okay? So going back to the original question, we have 1, 2, 3, 4 pi electrons. And then we need to ask ourselves, is this lone pair this one right here, is this going to be a part of that pi system? And if the lone pair is in a pi orbital, then yes. If it's in an unhybridized p orbital, then yes, it will be traveling throughout that donut of electrons that I like to call it, that is so special to the benzene ring, right? To an aromatic molecule. So what we have going on here is that the lone pair is in the unhybridized p orbital. Okay? And that carbon, because that carbon is sp2 hybridized. Okay? So the hydrogen is what's in the sp2 hybridized orbital. Okay? So if we are to include the lone pair, now how many pi electrons do we get? We should get 6. So far we have 6. Now where it gets tricky is where you have to look at what is called a hetero atom. Okay? So if a hetero atom is present, right, then we kind of have to make this decision, okay? So with heteroatoms, they have these 2 lone pairs. And a heteroatom is an atom that is not carbon, okay? Right, so your examples that you're going to see are going to be like sulfur, for example. You can see oxygen, right? Nitrogen and so on. But let's just keep sulfur and oxygen there in our list, right? So if the heteroatom is present, decide on a hybridization Okay, so if there is a heteroatom present, such as sulfur, such as oxygen, right, then you need to look at that atom and let it pick the hybridization, which will give you the molecule of the lowest energy or the most stable compound. And of course, your options, like it says in the question, are going to be aromatic, anti-aromatic, or non-aromatic. Okay? So when we're looking at this and we're trying to make that decision, we ask ourselves hypothetically, right? If I include that lone pair right there, the second lone pair, if I include that as a pi electron that is circulating within the ring like this, how many total pi electrons would I have? Okay? So what would our answer be? We would have 1, 2, 3, 4, 5, 6, 7, 8. Okay? We would have hypothetically 8. So if we hypothetically have 8 pi electrons in this system, we need to make a decision in terms of our Huckel's rule, okay? And Huckel's rule is just a formula, right? A formula that will let you classify a molecule as either aromatic or anti-aromatic, okay? And the formula for aromatic is going to be 4N plus 2. And for anti-aromatic, what is it going to be? 4N, okay? So what you want, and this is going to be equal to the number of pi electrons here. So let me put it like that. I'm just going to put all this in parentheses. Like that, okay? So what you want is so that the n is a full integer, right? 1, 2, 3, or 0. Let me put where n equal 0, 1, 2, 3. Basically, you do not want this, and so on. You do not want this to be a fraction. You do not want n to be a fraction, or it doesn't fulfill that specific rule. Okay, so Huckel's rule, let's see if we had 8 pi electrons in total. So we're filling in right here, an 8, right? And if we solve for n, right, are we fulfilling the rule where n is a full integer, or is it a fraction? So let's look over here. So your total pi electrons is 8 pi electrons, right? And you go over to for n, okay? You can substitute n for the letter n, you can substitute the number 2, and that would give you the total 8, right? So which rule does 8 pi electrons fulfill? Your answer needs to be the for n rule, right? Because for n, where n is 2, a full integer, is equal to the 8 that we found. So let's go back to our energy diagram, which shows the stability, the relative stabilities of these 3 different options. So anti-aromatic, where is that on here? It's the highest energy or the least stable. So if that is the case, this molecule here that we're trying to classify, if it can take a form at which it becomes more energetically favorable, in a sense, when I say that, I mean more stable, aka either non-aromatic or aromatic, it will. Now, it cannot be aromatic because it doesn't fulfill the 4n plus 2 rule, but it can make the decision to become non-aromatic by changing the hybridization of the heteroatom. So the heteroatom, the sulfur, if it takes on a hybridization of sp3, then it can no longer be included as either aromatic or anti-aromatic. It goes out to this third category, which is different, and it becomes non-aromatic. Because if it is non-aromatic, then it is more stable in comparison to the anti-aromatic, which is way up here in energy. So if that was confusing, I actually have a little diagram I think that I made in the past. That depicts how you can classify these molecules as one of the 3, and it kind of shows this little step-by-step process for you guys. So I can do the next examples following this. Let me see if there's a way for me to include this in our thing. Copy. So in order to do that, I'm going to have to add another page like this. I just think that this is so important, so I want you guys to feel really strong about it. Okay, so a molecule can be classified. You kind of make your way down here. You make your way, and you ask yourself, is it cyclic? Check. Is it planar? Check. Are all the atoms sp2? Check, right? If any of these are not, if your answer is not yes to any of these, then right away you go non-aromatic, okay? So that's what we have our dilemma here. And our dilemma here is that we have this heteroatom and it's giving us anti-aromatic. if the hybridization changes to sp3, right, and we do not fulfill this, the part about all the atoms being sp2, then the molecule becomes non-aromatic, and that is more stable, right? Lower in energy level than an anti-aromatic molecule. So we're going to put non-aromatic in our box, okay? Let's do the next one, kind of following that same trend, so I don't lose you guys. So let's count our pi electrons so far. Well, firstly, let's answer the question. So cyclic, yes. Planar, yes. All atoms are sp2. So a boron is always going to have 3 bonds to it. It's always going to be sp2 hybridized, and then a carbon with a positive charge is also going to always be sp2 hybridized. So those don't have an option. They all have unhybridized p orbitals, right? That's another way of saying this. And then now we have to make our decision between aromatic or anti-aromatic. Okay, so we kind of follow this route and we pick between the two. And what do we base that upon? Huckel's rule and counting the number of pi electrons. 1, 2, 3, 4. So we got 4 in total. So which rule does that follow? If we have 4 pi electrons, N can be 1, right? Full number of 1, and that follows the anti-aromatic classification, right? There is no atom like sulfur or oxygen where you can kind of make that decision in terms of the hybridization, okay? So it has to be anti-aromatic, and it's too bad, right? Now let's move over to the other one and follow the same idea. So cyclic, planar, all atoms are sp2. So far, we're going to have to look at that oxygen later on. So now let's go and look and count our pi electrons participating in the delocalization across this ring. So we got 1, 2, 3, 4. This right here, what type of orbital would you say that the lone pair is in? So we have an sp2. That's going to be an sp2 hybridized orbital. Why did I say that? Was because you have these pi electrons right here. Okay, so those are the electrons which are within the unhybridized p. Okay, so if we counted those so far, we have 4, right? Now we make that hypothetical decision with the heteroatom over there, the oxygen. If we were to include one of the lone pairs, what would be our number of pi electrons? We would get 1, 2, 3, 4, 5, 6. We would get 6 pi electrons, right? So if we, let me put 4 over here. So if we have 6, what rule do we follow in terms of our 2 different formulas? We follow 4n plus 2, so the molecule should be classified as what? Aromatic, okay? So this is going to take, this oxygen is going to take what type of hybridization, which will allow it to be aromatic. It will take on the sp2 hybridization that would fulfill these questions over here. Then we get aromatic, and that is perfect for us, so we can put aromatic in the box, okay? So that's just like a benzene. So that's extra stable, just like a benzene would have 6 pi electrons as well. So now let's look forward to the next one and kind of take that same procedure. Now what I see here when I'm looking about all the atoms that are in this ring, I see this. So I like to just draw out the resonance structures for this. So try drawing out the resonance structure on your own, where the pi electrons come up onto the oxygen, okay? And when it does so, what charge do you get on the carbon? Get a positive charge. So the positive charge has now been displaced down to the carbon. So now let's ask ourselves, and of course we have a nitrogen here. So let's ask ourselves in terms of these rules that we had up here, cyclic, planar, all atoms sp2, and so on, right? So I'm seeing sp2, 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 and then the nitrogen, this lone pair, remember, it's got to come in because it's in a pi orbital. The H is in the sp2, is bonded via an sp2 orbital, and this right here, the lone pair is in a pi orbital. So that's going to come in. So what's the hybridization of that nitrogen? It's also going to be sp2 hybridized. It takes the lowest one. So for that reason, we have fulfilled all these rules kind of over here. And let's count the number of pi electrons from that. So we got 1, 2, 3, 4, 5, 6, right? So when you have 6 pi electrons, which rule is that going to fulfill in terms of our Huckel's rule? And I even put it up here for you guys. So we got 4n plus 2, so it's going to be aromatic. Perfect. Okay, so we put aromatic in our box. So again, if you guys have any questions about this, hopefully at the beginning when I started talking about orbitals and stuff, you didn't get too confused. But please just ask if you have questions about that, okay? And that's the document, which I will post. Now it says rank the following substituted benzene compounds in order of increasing rate in an electrophilic aromatic substitution reaction. Okay, so electrophilic aromatic substitution, you'll see it denoted as EAS, right? And that's what the letters actually stand for. So this is just a reaction that's going to occur between a benzene or some benzene derivative, something some substituents attached to a benzene, where you have a very strong electrophile, right? A very strong electrophile that's going to react with the benzene and substitute one of those hydrogens with the electrophile itself. Okay. So that's the whole point. So in the name, you'll see EAS, you'll see NAS, right? And I made 2 videos about this earlier if you want to go see them. But EAS, the E, the letter in the name, the first letter, or the first word in the name, is telling you what gets substituted onto the benzene ring. So if the benzene ring is getting substituted with an electrophile, the benzene itself must be acting as what? A nucleophile. So the benzene itself is acting as a nucleophile. Okay? So you could have different groups upon this benzene which are going to change the reactivity of the benzene. Okay? We could have electron donating groups or electron withdrawing groups, okay? And these can activate or deactivate the ring in terms of proceeding in this type of reaction, okay? So in the EAS reaction, you want your benzene ring to be more nucleophilic, right? That would allow this to proceed. So what type of groups would we want to have on the ring? Donating or withdrawing? So your answer should be donating, because if you have electron density going towards the ring, that's increasing its nucleophilicity and it's allowing it to act as a nucleophile, and the reaction will proceed faster, okay? So we need to look for things that are electron donating groups, right? So when I'm just looking at these, I like to fill in the lone pairs. I like to fill in the charges because they might not be shown to me. So I'm going to fill in 3 bonds to a nitrogen means that the nitrogen has a lone pair. So that's what we have. What about 4 bonds to a nitrogen? What's the charge for 4 bonds to a nitrogen? Should be positive, okay? So let's look at what is directly attached to the benzene ring. So this is the carbon of the benzene ring that has that group coming off of it. And ignore the bottom side just because that's the same throughout all of these. Look at this carbon, and look at this carbon. And we're gonna look at the atom that is directly attached at that carbon, okay? And we're gonna rank these. So the fastest is gonna be the one that's the most electron donating, right? And electron donation can occur, and withdrawal can occur via two effects. What are those two effects? Resonance and induction, right? So the one on the farthest right, is that electron donating? And if so, is it via resonance or the inductive effect? So if it has a lone pair, you don't have to memorize these, you guys. If there is a lone pair directly attached to the benzene ring, that is donating, and it's donating via resonance, just like that, right? So you see how those carbons are now becoming more, right? They're becoming more electron rich. So that's going to be activating this molecule, okay? Now let's compare to this one in the middle. What do we have directly attached? We have a carbonyl carbon, and what charge does that have? It's partially positive, remember? So is that going to be electron donating or withdrawing? If it's partially positive, it wants to actually, it is electron deficient. So it is trying to pull electron density towards itself to stabilize itself. And as a result, that is going to be an electron withdrawing group. Okay, let's put this as electron donating group. And then let's compare it to the one on the very far left, right? What charge we have there? Full positive. So is this withdrawing or donating? This is definitely an electron withdrawing group, you guys, because it has a full-on positive charge. The other one had a partially positive charge, and this one has a full positive charge, okay? So this is a stronger electron withdrawing group in comparison to the carbonyl that we have on the middle, okay? So given that we identified all of that, how are we going to rank these guys from left to right? Which one is the most deactivating? So deactivated. So which one's going to occur at the slowest rate, or number one should be the very far left. Then we're going to go to right here. It's electron withdrawing, but not as strong as the one on the left. And then on the right, we have a full-on electron donating group. So that's what you would want to have on your ring when you are undergoing a electrophilic aromatic substitution, okay? And I have a timeline for those that I could possibly share as well. Now, rank the compounds in order of increasing reactivity in an SN1 process, 1 being the least reactive and 3 being the most reactive. Okay, you guys, so I'm going to give you a disclaimer that this question is another question that is asking you guys about aromaticity. Okay, so aromaticity is a very big concept on this exam. I mean, I cannot stress that enough. More than one fact question will ask about it. It will be on that ACS exam. So make sure that you feel confident about it. Don't get scared by the fact that there's SN1 being introduced, which is also important, I would say. So let's go over SN1 process. S stands for substitution. N stands for what? Nucleophile. And 1 is going to stand for what? Unimolecular, right? So if this is unimolecular, meaning the rate is dependent on one molecule, right? The formation of that carbocation, right? Dependent upon that alkyl halide and how likely it is to form the carbocation. Then that means that can serve as a reminder to you that an SN1 process occurs in how many steps? 2 steps. And in our first step, what did I just say that happens? Leaving group is going to leave, right? So leaving group is going to leave. And when the leaving group leaves, what are we going to form? A carbocation, right? So it's just going to be this. We assume all of these have left. And we put a positive charge. Positive charge. Okay? Given that we put that positive charge there, now we need to compare these guys in terms of their stability. The one that is the most stable, right? So the more stable the intermediate, right? The more stable the intermediate, the more likely that leaving group would have left. So the more reactive the original alkyl halide. So you need to be looking at the stability of the intermediate, and that would let you know about how reactive that original molecule was. It's the original molecule, okay? So this is asking us about aromaticity. Let's look at the first one, for example, right? If we're looking at the first one and we go up to our rules, cyclic, check. Planar, check. I don't see why it wouldn't be. Are all atoms sp2 hybridized here? Your answer needs to be no. That is an sp3 hybridized carbon. So what would the classification of this molecule be out of our three? It would be non-aromatic, right? Okay, so we know that non-aromatic lies in the middle in terms of stability, but let's go and look at our other ones and make our decision at the very end. For this one, cyclic, planar, sp2 hybridized atoms, let's count those, right? 6 pi electrons. So what should our answer be in terms of our classification? Should be aromatic, right? Okay, that's really good. That's very stable. So most likely, that's going to be number 3. Now let's move forward to the next one. Fulfills all those same rules at the beginning, right? And what we get, 1, 2, 3, 4, 4 pi electrons. No hetero atoms, cannot be changed, right? So for that reason, this is going to have what classification? Anti-aromatic. Okay, and we know in terms of our energy diagram, which one is the most stable out of these? Aromatic. So which one would have been the most reactive original alkyl halide? The middle one. Which one would be next? The left one. And of course, the right one would be our least reactive alkyl halide in an SN1 process. Okay, so you see how this is like a 2-step type of question. You got to know 2 different concepts. SN1, that will keep coming back, and then also classification of aromatic, non-aromatic, as well as anti-aromatic compounds, okay? Now let's move forward to number 4. Place the following compounds in an increasing amount, in order of increasing amount of hydrate, that's important, present at equilibrium in the reactions with water. Okay. So we have these 3 different molecules. And now this part has not been talked about in the lecture yet. Okay. This should be, I'm not sure what Dr. Bean's going to end up doing, right? Right now I'm recording this and it's Monday, so I'm not sure what's going to happen. But at the point that I'm recording this, it has not been talked about yet. So I'm not even sure if it was supposed to be on the exam too, if it wasn't gone into. But let's still do it, okay? It's still a good question. So in terms of what is a hydrate, I would say that is important. So hydrate is going to be something characteristic. You're going to see a molecule that looks like this of some sort. I'll put 2 arbitrary R groups on that carbon. So if you have this, an OH and another hydroxy group directly attached to the same carbon, that is known as a hydrate, okay? Gets its name from water, okay? And basically what you have here is if you have if you have a ketone or an aldehyde of some sort. Right now I'll put a ketone with 2 arbitrary R groups, for example. That could be anything, right? We're talking aldehyde or ketone here. we have a reaction that happens with water, and particularly this likes to be acid or base catalyzed, right? So you're not going to see just H2O here. You're typically going to see like, oh, I wish the eraser wasn't so big. You're typically going to see, for example, H2O plus for acidic conditions, and what would you see for basic conditions? You're going to see OH minus, right? So one of these two is going to help to give you that hydrate, okay? But let's ignore what type of catalysis is happening here, what it's being catalyzed by. Well, ignore that. I mean, it doesn't really matter for the purpose of the question. What matters is that we're going from this ketone on the left, we're adding water, and we are forming what is called a hydrate, okay? So in terms of stability, what do you think about the hydrate? Do you think that is typically stable or unstable? So that is typically unstable, okay? So when we're asking ourselves about equilibrium, remember there is a forward reaction, and that has a rate, and then there's a backward reaction, and that has a rate, and when the rate is equal, right, we're at equilibrium. So we want to ask ourselves, where does the equilibrium lie? So what would be present in a larger amount or a higher concentration when we are at equilibrium, okay? And the equilibrium, this is just a general rule of thumb. The equilibrium lies towards stability, right? And you can say stability or less reactive, for example. So that's the side that this arrow, so remember we have these bidirectional arrows, and we want to figure out, is it like this and like that, or the opposite way around, where you have this is the longer arrow and that's the shorter arrow, right? That would be an example of something that lies to the left, and you're going to have a higher concentration of the carbonyl version at equilibrium, okay? So in order to figure that out, remember, it goes down to stability. So we're going to have to compare these three molecules relative to one another and consider their stability and actually their reactivity. All right, so I like to think of it as reactivity, actually. I think that's an easier way to conceptualize this. So if we're looking at the carbonyl on the very far left, right, we need to consider two factors for all of these, actually. What do you guys think could be those two factors to figure out how reactive that carbonyl carbon is in order for an H2O to come and attack it? Could be an H2O under acidic conditions, could be an OH minus under basic catalyzed conditions. But regardless, we're just talking about its susceptibility to nucleophilic attack right there. So the two factors that you want to look for are going to be the positive charge of carbonyl carbon and also crowding, slash steric hindrance of that site of attack. So if we're comparing those two factors between all of these, right, I see in the middle one, there's a chlorine, which is going to be acting via the inductive effect. And also, this one as well. The one on the very far right doesn't have that, but the two on the left do have that. And in addition to that, what's different between the middle one and the left? What's different between the middle one and the left? I'm going to ask you guys. So the one in the middle, in terms of the group that's attached here, right? So here we mentioned like two R groups, right? But we're just talking arbitrary groups, not necessarily carbon chains. So if it's a hydrogen, how is that going to have an effect on steric hindrance or crowding? So there's less crowding, right? Meaning that this middle carbonyl is going to be the most reactive, right? Because it has this inductive effect at play, which is increasing the partial positive charge, withdrawing electron density, right? So it's increasing the partial positive charge of that carbonyl carbon, and there's also less crowding. Does that make sense? So in terms of reactivity, the middle one is the most reactive, right? So if the middle one is the most reactive, that means that more, the equilibrium is going to lie more to the right, towards the high hydrate, okay? Because this is more reactive, aka less stable. And equilibrium lies towards stability. Now, what do you guys think between the first one and the third one, given all that knowledge? So I would go with the first one being number 2 and the third one being number 1, because what's the difference between these two? So the difference between these is that this one has the chlorine and this one does not. So this just has the 2 R groups. This has R groups, but this has the chlorine. So it's acting via the inductive effect, withdrawing some electron density. So how it's influencing the reactivity is in terms of making the charge on that carbonyl carbon, it's making it more partially positive, therefore more susceptible to attack here by an H2O. So that's why this one would be number 2 and that one would be number 1. Again, feel free to ask any questions about these. And even if you want to refer to something in the comments afterwards, if you can't watch it at the direct time that I set it to premiere, that's totally cool. Ask there and I'll keep up with the notifications and stuff. So number 5, we want to rank the compounds in order of increasing reactivity in an SN2 process. So look how much Orgo-1 has been introduced here, right? Has been asked about here. So we have SN2, and what does that stand for? The 3 letters. So if it's bimolecular here, the rate determining step is dependent on both the nucleophile and the alkyl halide. So that means that these are happening in the same step. So that means how many steps happen here in SN2? This is a 1-step process, okay? So is there the formation of an intermediate? No, there's no formation of a carbocation intermediate. However, even within that 1 step, of course, there's going to be a transition state. So we need to look at the energy level of that transition state, how stable it is. The lower the transition state, right, in terms of energy level, the faster this reaction is going to proceed, aka the more reactive it is in an SN2 process. So we're basically looking at activation energy here. If we're going to draw a little diagram. Activation energy, this is the energy of the transition state, for example, okay? Not an intermediate. So we got to rank these. So let's consider, with all of these, we're going to have some sort of nucleophile, so some strong nucleophile. Okay, just think of any strong nucleophile example. And that's going to come, try to attack, push off the bromine. It's going to try to come and attack and push off the bromine. Can that even happen for this one, for the middle one? So it can't happen, and why can't it happen? So this thing is going to keep coming back and coming back. So no SN2 on sp2 hybridized carbons, okay? So the unhybridized P gets in the way of that nucleophile from coming and attacking, okay? So far I'm thinking that this is going to be number 1, but let's not put it yet. Let's move forward to the next part. So here, same idea, strong nucleophile. It's going to try and attack right here and push out the bromine, okay? So that's not sp2 hybridized, so that can occur. So right away, which one are we going to put as our number 1? So we're going to put the middle one as our number 1. And now let's compare between the left one and the one on the right. So I would say that this is probably the trickiest question, I would say, in the fact section. To be honest with you, I remember in 2019, a lot of students came back asking questions about this. So basically, what's different between these two? They're both adjacent to pi bonds in general, but the location of where that leaving group is what is different. Okay, these are both secondary. Remember, so in terms of degree of the alkyl halide, what is the trend for SN2? So that's your trend for SN2 in terms of reactivity. Here we have 2 that are secondary, and on top of that, both of these have some sort of resonance. You know, in the sense, I wouldn't say resonance is the correct, exactly accurate term, just because we're talking about a transition state, but you can think of it as a pseudo carbocation, where you have a positive charge here, right? And if you were to do that, then you could draw resonance of this coming here, and so on, right? And then over here, you could draw this here, and then the positive, this going here, and this going here, and this going here. You see what I'm saying? Now, there is something very special, and I believe, this was mentioned in the notes, but it was, briefly mentioned, and that is that if you have, a leaving group of some sort that is at specifically this position, and that's called the benzylic position. Then it is more positive. Benzylic position, then it is more reactive in an SN2 process. And that's just because of having the transition state where this bromine is leaving, right? And then the bond to the nucleophile is forming, on the other side and so on. And you're putting at one point where this is leaving, and then you're adding, some negative charge here and positive charge towards the. You can think of it in a sense of forming a carbocation, but that is going to be more stable in comparison to if you just had like that, for example. If you're comparing that to the benzylic position where you have this, okay, like the benzylic position with a partial positive or with a positive charge is more stable, okay? So your transition state is lowered in energy. Therefore, this one is going to be the most reactive, and then would come this one following it, okay? And that's a similar idea to reactivity in general. Like if you're talking about a Grignard, for example, a Grignard is able to attack, like if you had this, for example, a Grignard could go and attack here Okay, so whenever you have the leaving group adjacent to pi electrons, oops, that really helps out in terms of the reactivity of that alkyl halide, and it's even more so when that leaving group is at the benzylic position in particular. Okay, and draw out the resonance for that, even though it's not a carbocation that's forming, but draw out the resonance for that if you want to see more. Okay. All right, so let's do reactions here. And it is saying it wants us to provide the major product, indicate the stereochemistry, if applicable. Full credit is awarded only when the product of each step in a multi-step reaction is shown below the reaction. Okay, so let's get started with the first one. What we see is called sodium dichromate, H2SO4, and high heat. Okay, so you guys have seen sodium dichromate before when it came in Orgo 1 as an oxidizing reagent, and you're also responsible for it for the first exam of Orgo 2. It was an oxidizing agent, and it was introduced, however, it was written a little bit different than what we see here. So this is different from, let me write, sodium dichromate like that with H2SO4. And here I'm going to add water. So it's going to be dilute. It's not going to be as concentrated, first of all. And as well, I'm not going to include heat. Okay, so that is different from that. Okay, these are two different things. They're the same compound here, right? The same molecules involved. However, one is dilute, the other is concentrated. So which one do you think would be harsher? Which one do you think would do something harsher when you're comparing between the two? The one with the heat that's concentrated, or the one without the heat that's dilute? So definitely this one is going to be harsher conditions, okay? So what we're referring to is a benzene ring here that has these three different substituents coming off, okay? And you add sodium dichromate, high heat, in acidic conditions, and that has the ability to cleave off. So it has the ability to actually break carbon-to-carbon bonds and oxidize them all the way to a carboxylic acid when they are present on the benzene ring. So for example, we're looking at this benzene ring here, and this could be an alkyl chain of 50 carbons, and it is still able to cleave right here and remove everything else that follows and change that to a carboxylic acid. So like I'll write it like this, and we have acidic conditions. So in terms of our carboxylic acid, right, this is going to be actually the carboxyl group is going to be protonated because we have acidic conditions. So that acid over here would be responsible for protonating this. Okay, so it's not going to be deprotonated in its carboxylate form like it would be if it was under basic conditions. Okay. And then we have an ether and we have a tert-butyl group. So is this going to react with the ether, you think? And do the same thing? So your answer should be no. It's not going to cleave off the ether like that. Ethers are pretty unreactive molecules, and that's why we didn't learn too many reactions with them, right? You gotta have, remember, you gotta have a very strong acid, such as in the last unit we had like HBr, HI, those guys, etc. You know, strong acid catalyzed cleavage of the ether, right? We're not going to have that over here. You know, this has like more negative pKa values in comparison to H2SO4 anyway. And then what about the tert-butyl? What do you guys think? Is this going to react with the tert-butyl? So it's not going to react with the tert-butyl group. This bulky group is not going to react. However, if I were to give you guys some examples, for example, here, you guys, if you had a molecule like this that I'm showing, and you use this reagent, the sodium dichromate H2SO4 and heat, you're going to be able to cleave off any carbon-hydrogen chain like this. Even if it had a carbonyl in there, it's gonna cleave it to the carboxylic acid like this. The tert-butyl group gets untouched. So if you want the tert-butyl to still be there, you would definitely want to do this. That's convenient. This gets cleaved. As with the alkyne, the ether is left untouched, okay? And that's under the acidic conditions that we're going to have this going on, okay? So then, now that we got that going on, what is number 2 going to do? Any thoughts? So number 2 is going to affect this carboxylic acid over here. So is OH right here, is that a good leaving group? No, it's not a good leaving group. So if you want to replace it with something that is a good leaving group, you can use this SOCO, SOCl2. You can replace it with a chlorine to make an acid chloride. And you guys will talk about this when you get to carboxylic acid derivatives, like an acid chloride, that acid chlorides are the most reactive, right? So they are very reactive, and you're taking it from a carboxylic acid to something that is more reactive. And why is it more reactive? Two different factors, but the main one here is that you have a good leaving group on that molecule. Okay? So that's what you would get from that. And then for step number 3, what type of reagent is this? What is this called? So this is called the Gilman reagent. And the Gilman reagent is particularly going to react with these acid chlorides. Okay? And you may remember this from Orgo 1 if you covered the Corey house reaction and the Corey, the reagent used there. So you have these 2 alkyl groups. You see the big 2 here? You have 2 of them, but only one is going to add. So don't let that confuse you. Only one is going to add. And what you're going to do is you're basically going to replace the chlorine there with whatever that group in parentheses is. So, am I right? Everything else the same? Like here's our carbonyl, and just replace it with a CH2 and the phenol. Okay, so that's what you would get from that, the Gilman reagent, and just a cute way with the letters to remember Cl. That's going to be specific to your acid chlorides, right? This is not going to react with the the carboxylic acids. That's the whole reason why we had to do the number 2 step in order to replace it with the acid chloride, the chlorine. Okay. So now let's work on number 2. And we have these aromatic rings. We have 2 of them. And on our arrow, we have HNO3 and H2SO4, right? So we have this mixture. These are added at the same time. And you guys will do this in lab. Well, now you won't do it in lab, but for Orgo 2 lab, you're supposed to do this in lab. So what you have going on here, you have this mixture of HNO3 and H2SO4. So if you were to draw out, you know, what these look like, I can try to do it very quickly. So sulfur can have how many bonds? Can have 6. Like that. Okay. And, or that's sulfuric acid. Okay, H2SO4. That looks good. And then let me write for you guys. The nitric acid. So both of these have acid in the name. So both of these are typically associated as strong acids. So let me check that real quick. We have 1, 2, 3 oxygens, and then 1 proton, and then neutral charge. Okay, perfect. So that's your nitric acid, and that's your H2SO4. So between these two, which one is the stronger acid, you'd say? Like if you had a mixture of these two, which one would act as the acid because it's a stronger acid? Right? The terms acid and base are relative terms, so it depends on what else you have in that mixture, right? So definitely the sulfuric acid is the stronger acid. So that's going to be acting as the acid. It is going to go and, it is going to give off its proton because it's the acid. So you're basically going to have the nitric acid. Oddly enough, even though it has acid in the name, it's going to act as the base and it go and abstract a proton. When it abstracts that proton, you form water as a good leaving group right here, right? And then you're going to have this come down, push off that water, and you're going to form the nitronium ion. So that's what I would say is important, especially for the lab midterm and such. Knowing that you form this nitronium ion where it has a full-on positive charge, right? So what is the umbrella term for this type of reaction? Like we called it nitration. There's 5 different, well, I'm going to give you guys the answer now, but there's 5 different EAS reactions that are mentioned, and this is one of them. So this is electrophilic aromatic substitution. So you definitely want to be able to identify that. So that means you're adding this electrophile onto a benzene ring. So if we're undergoing EAS, right, we talked about this in the fact section. For undergoing EAS, your benzene ring has to be acting as what? An electrophile or a nucleophile? So the benzene has to be acting as a nucleophile, right? So if it's acting as a nucleophile, does it help to have electron withdrawing groups or electron donating groups? It helps to have the electron donating groups because those increase the nucleophilicity of the ring, allowing for it to react. So those are what, you'll hear people say activating groups, and I prefer to refer to them as electron withdrawing or electron donating, right? Just because we also have NAS, but so what's activating here would be deactivating there, like it's vice versa. So I prefer to just say electron withdrawing groups. Those are going to help out. So which ring is more, you know, which one is more activated here in terms of this reaction, EAS. So it's definitely going to be the one on the left because you have a electron donating group via what effect? So it's going to be electron donating via resonance. You have that ether over there with the lone pair. And then you need to ask yourself, we're trying to add this NO2 group onto the left benzene ring, right? So how is that going to direct? It's going to direct that substituent onto the ring at a particular location, and you have to decide that. So this right here is going to direct either to the ortho or to the para position relative to itself. So let's denote those. So you have the ortho, you have the other ortho. So the ortho is the one directly next to. Then you have the meta, and then you have, over here, you have the para position. Okay, so we have to make that decision, and we have 2 ortho spots, and we have 1 para spot, right? And right here, which spot would you guys say is least sterically hindered? Right, like the least amount of bulky groups beside it, or groups in general beside it. So your answer should be, well, I mean, there's no way for you guys to point it to it, but basically between the left and the right, or here, let me put the blue, the red, and the black. So which one do you guys think it's gonna go? So I would say it's going to go to the blue position. It's going to go to one of those orthos because there's 2 orthos and there's 1 para, and one of the orthos, so the red ortho and the blue and the black para carbon, those spots have that bulky group beside it, and the ortho one has 2 groups beside it, versus the blue ortho position does not have 2 groups. So that's what's going to lead this to go to the ortho blue position. Okay, so I would put that nitro group over here and then basically leave everything else the same. You know, so typically when there's let's say you have 2, you know, ortho spots, you have 1 para spot, you consider the probability of 2 being more likely than 1 spot, right? But then if there's steric hindrance involved, that's when you really got to consider this a little bit further and take it that step further. Okay, and forget about the probability as much. Okay, so that's where the nitro group is going to go. Let me know if you have any questions about those. Those can be tricky, but definitely a benzene ring is going to be considered bulky, okay? Now let's move over to 2. So you have fuming H2SO4, and that means that you have very concentrated H2SO4. You know, this strong acid, it's concentrated, and you also, in there, it's going to have some SO3 formation. And so what you're going to be adding onto the benzene ring, is this EAS or NAS? It's going to be EAS. So you'll notice with these EAS reactions, remember, you're going to have a very strong electrophile in order for it to react with the very stable benzene. Okay? And it's trying to, the benzene's trying to act as a nucleophile, but it's stable. So what we have is, you know, I believe this is called sulfur trioxide. Correct me if I'm wrong, but that's our electrophile for this type of reaction. And what we have going on here, you know, basically the benzene ring is going to gain that group. It's going to give it a sulfonic acid functional group. And of course, you know, we have these 2 benzene rings, so you have to make the decision of which one you think is going to react. Who thinks that the left one is going to react more than the right one? Like, which one do you think is going to react more? I'll put both of them in here. So the one on the left, your answer should be the one on the left. And the reason why it's going to be the one on the left is because the one on the left has the electron donating group, which is activating in the case of EAS. It does have the electron withdrawing group. However, the one on the right only has an electron withdrawing group and does not have the strong electron donating group that the left one has. So that's why it's going to be that one, okay? This is going to be contributing, okay? So now we have to make the decision, and when we have, when we have two substituents on the ring like this, I kind of just ignore everything except for the strongest and most electron donating group, because that's going to carry a weight. If you have two substituents that are directing in different directions, like the electron withdrawing groups direct which direction? Meta. So, and this is going to be ortho-para, like we said before. So when we have that situation, I just ignore the other group and you pay attention to the one that is the most electron donating that is attached to this ring, okay? Of course, this is more electron donating than that benzene ring that's attached on the other side. So it directs ortho-para, so let's kind of highlight our options here. So ortho-para to that, one of the ortho positions already taken, right? And then that is our para position to our methoxy group. So which one do you think it's going to go? The ortho or the para? So I'm going to add it to the para position. Add the sulfonic acid there. And the reason why I picked that is because in terms of probability, you have a 1-to-1 ratio, of ortho to para spots, just because the other, I'm going to put meta direct, right? Because the other ortho spot is already taken up by the nitro. So now you have like a 50-50. And so the one that has the least steric hindrance is going to be your answer. And that is the para position, because look at all this space. You have an empty space next to it versus over here, you don't have the empty space next to that blue ortho position, okay? So I'm going to put the sulfonic acid functional group right there. Okay. Now for question number 3, we have a benzene. We have a nitrile in the benzene. And then on our era 1, we have a Grignard reagent. Okay. So what do you guys think would happen? We did this like in Orgo 1 even. In the facts section, they would ask, does a Grignard reagent, does it form in the presence of a nitrile group? So your answer should be no, because there is a dipole moment between the carbon and the nitrogen due to the nitrogen's electronegativity, right? So what would happen between a Grignard and a nitrile? They would react with each other because this is such a strong nucleophile that it would react with the nitrile, the carbon there. It's going to go and attack there, okay? And I would love to see if I can, use this. And I want to draw out that nitro group because it's important. So I'm going to draw the nitro group for you guys. And that carbon is very susceptible to attack by a Grignard. So that's what's going to happen here. You're going to have the Grignard go and attack that carbon of the nitrile. And then can carbon have more than 4 bonds? We're forming a bond here. So it can't. So what do you guys think is going to happen? So the pi bond is going to break. Excuse me. So the pi bond is going to break, and it's going to go on to the nitrogen, okay? So everything else is the same pretty much. One of them broke. This goes like that. Then you gained a lone pair, right? So what is the charge of the nitrogen? Negative, right? And then now you have the attachment of that carbon. So this is a way to form carbon-carbon bonds. So now you have a CH2, CH3 attached at that carbon of the nitrile, and you now formed a minus charge on that nitrogen. Now, you'll see, like, for example, you'll see in Dr. Bean's keys and such, if they're written by her, you'll see her sometimes, you know, if the 1 and the 2 step are shown separately, you'll see her in after the number 1 step, she will put that magnesium and that bromine there, you know, acting as the magnesium acting as a spectator ion, because magnesium likes to have what charge in its cation form? In its cation form, it likes to lose 2 electrons. Okay, if you look at where its location is on the periodic table, you'll see that it likes to be 2 plus. And here we have 1 minus charge from the nitrogen. And you have 1 minus charge from the bromine. So that means that this magnesium can be balancing out both of those. You know, so if I'm putting it combined with the bromine, which is a -1 charge, then that's 1 of the 2 plus. So you still have a +1 on there, and that's what's balancing out the nitrogen, okay, with the minus charge. You could also, if you really wanted to, show this as magnesium, 2 plus, bromine 1 minus, and then nitrogen 1 minus. But she likes to show it as such, so I'll put it like that. Okay. Now, the parts that happen after this, it's a very lengthy mechanism, and I think that you guys will be a bit responsible for it towards the end of Orgo 2 when you're talking about the carboxylic acid derivatives, because a nitrile is a carboxylic acid derivative, believe it or not, and I think she's going to show this mechanism in the notes. But as for now, for exam 2, the mechanism is not discussed, and you're not responsible for it, so don't worry about it. But this H3O plus step, the second step, you know, it's a lengthy mechanism, but at the end of the day, what happens and what you guys would have to put on your exam for now would be that everything else stays the same, except the carbon that has the nitrogen attached to it with the minus, that is going to be converted. So let me highlight what I'm talking about. That is going to be converted with this H3O plus. It's going to be converted to a carbonyl carbon. Okay, so that becomes the carbonyl oxygen. Okay, everything else remains the same. That's what happens with the H3O plus step. Now, if she showed it where 1 and 2 were shown in the same, step, like you had CH3, the Grignard reagent, then H3O plus, written under number 1, and it wasn't shown as number 2. It's a whole different step or number. Then you would go straight from, let me indicate, from here, you go straight to this, and you would ignore this middle part, okay? If that were to be the case. Sometimes she likes to do that, okay? So keep your eye out for that. And then for step 3, we have this really weird looking reagent. It's bulky. It has these 3 benzene rings. Oh my gosh, 3 benzene rings attached to it. And a double bond. So this is a way, this is called the, hasn't been talked about yet, but it's called the Witting reaction, in which you have a molecule that is classified as a yllid, so it's spelled very odd. So you have a yllid involved here. And what a yelid is it is a compound that has opposite charges on adjacent atoms. So like right here, you guys see this carbon and this phosphorus. So if we were to draw this in such a way that, you know, it's a resonance structure to this. Let me put it for you down here. So we'll put the benzene rings. You know, there's 3 of them. And the benzene rings are attached to the phosphorus. We have a carbon with a hydrogen, as well as another benzene ring. And then in addition to that, so you see how there was a double bond up here? So if that were to go onto the carbon like that, we would get this, right? Minus charge. And then what would be the charge of the phosphorus? Yeah, so the phosphorus valency of 5, right, likes to have, and here we would have a positive charge on it. So that is an example of a yelid. That's just a term when you have adjacent atoms in a molecule that have opposite charges, plus and minus, okay? So when you have this yelid here, what you can do, and this is very easy in the reaction section. I mean, all you got to do is, here, let me try to do this. If I can screenshot this. Let me copy. Very easy in terms of the reaction section, like that. So you kind of flip this upside down and you move it with your hands, and you're basically going to connect the double bond and you're forming an alkene here. This is a way to form an alkene. So like if you went like this, let's erase. What you're doing is you take the double bond right here, and you smush it to the double bond of the carbonyl. And then that's how you would get your answer. Like you basically bring this and this together and you form a double bond right in the middle. And I'll show you that right over here. I will show you. So this is going to be the carbon of the carbonyl on the left. This is going to be the carbon of your yelid on the right. And let's put our benzene and then whatever was attached there, so the hydrogen. As well as what we're going to put is the groups that were attached about that carbonyl carbon. So this is a very selective way to form double bonds, more selective than E2, the E2 route even. So we end up with that. Now, in terms of our stereochemistry, what did I put our stereochemistry as for our product? Like, is it trans or is it cis? So this answer is trans because our bulkier groups are going away from each other in the space. Like this one is going up, this one is going down. And so I did that on purpose because that would be like a point off or so for not indicating that the winning reaction gives you a trans product. Okay, it is more favorable to be in the trans orientation, right? It's more stable, that final product, so it's more likely to occur that way. So you want to make sure that you put it trans. You know, if not, you could get -1. Okay. So hopefully the Witting reaction isn't too bad. You're forming alkenes and you smush the carbonyl and the ylide together to give you that double bond. I'm gonna wait for like a couple seconds just in case if somebody has questions. All right. So let's continue on and see what we have here. So we have a bromobenzene and we have this acid chloride with AlCl3. So what reaction do you guys think is happening here? So it's Friedel-Crafts. Is it going to be Friedel-Crafts alkylation or acylation? So this is going to be Friedel-Crafts acylation. Okay. And the umbrella term for this reaction, right? So remember we said there's 5 of them. It's where the benzene acts as a nucleophile. The electrophile has to be really strong. It's what gets added onto the ring. So that is called EAS, which stands for electrophilic aromatic substitution. With this EAS reactions, you're typically going to see them, right? You can see it as the nitration mixture as what we had above. Or you can see it, you're going to see these commonly in the presence of something like this. So this, do you guys think that this is a catalyst, but do you think this is a Lewis acid catalyst or a Lewis base catalyst? So based off looking at the structure, right, the aluminium is electron poor, okay? This is more likely to be attacked by something else that has a lone pair, right? So this is a Lewis acid, okay? Definitely a Lewis acid, something like NH3 with a lone pair can come and attack it, okay? So when I say Lewis, we're referring to the electrons, right? So it accepts electrons. Okay, so this is not a Bronsted acid, which deals with the protons, okay? Now that we got that out of the way, this is your acid chloride. So that's what's going to get added onto your benzene ring. And that's where you have to worry about directing the groups that direct on your benzene ring. So you have this bromine. So is it bromine going to be, ortho and para directors go hand in hand, right? So if something directs ortho, it also is going to direct para. And you have to make that decision yourself. And then if something directs meta, right, it only directs meta. So a little trick for remembering that is this is your electron donating group. So it's duo, dos, two. It's going to direct ortho, para. Together, both ways. And if you have an electron withdrawing group, for example, if you take the W. Just a little trick to help you to remember, because there's a lot of stuff to remember. And we flip it upside down. What letter we get? We get an M. So that, oops, why is that happening? We get an M, and that's going to stand for what? Meta. Okay, so electron withdrawing groups direct to the meta position. Electron donating groups direct to the ortho-para position. Now here we have a halogen. So how do halogens direct? They are the exception to this rule because they act via the inductive effect to withdraw electron density. So you would think, right, they're weak deactivators, you would think that they would direct meta like electron withdrawing groups do. However, they are the exception because they have the lone pairs on them, which can come into the ring and can direct to the ortho or the para positions. Okay, so resonance is the factor at play that is helping for this to direct ortho para, and you can look in the notes to see the structures, the resonance structures, and so on. It's really not important, but what is important is knowing that they are the exception to the rule. You have these two, counteracting forces. Resonance, that's donating a little bit, but then you have the inductive effect, which is withdrawing. So in terms of directing, though, halogens are going to direct ortho-para, and I would call them a weak deactivator. Okay, so they're not like electron withdrawing groups such as a nitro or something with a full-on positive charge. Okay. So they direct ortho-para. So let's highlight our ortho. Here's our para. So that's what we have to figure out is where this electrophile is now going to be added on to our benzene ring. Okay, and it's going to get added on like this is our electrophile here at play. We have this. Okay, very strong electrophile. And you can draw the resonance structure for that, of course. The acylium ion, look it up, and it's another resonance structure. Actually, the more stable one. So, we put this as our number 1. And we have this. The bromine, nothing happened. It's directing to ortho or para. So what do you guys think? Do you think it's going to go ortho? There's 2 ortho spots. Or do you think it's going to go para? So it's definitely going to go para. And the reason for that, I mean, first of all, you want to consider probability. So you see a 2-to-1 ratio in terms of how many orthos versus how many paras. So you would think it's going to go ortho, right? But then think about the steric hindrance involved here. So you have a cyclohexane ring, a full 6-membered ring that's just like the size of a benzene ring, right, in terms of the number of carbons there. And you're adding that onto this. So that's classified as a bulky group. So I'm going to put here and say this is bulky. So because it's bulky, that's why we're going to send it para. Right, so steric hindrance becomes a larger factor at play in comparison to the probability. So we attach everything. Bromine is still there. And that's what we get for step number 1. Oops, why did I do that? Okay, so now let's look at step number 2 and see what we have. So we have, what do you guys think? Do you think this is an electrophile or a nucleophile? The CH3O minus. So the CH3O minus, it has a minus charge, right? So it's going to be a nucleophile. It's a good nucleophile, and we have high heat. Right, so we haven't talked, for this exam, we haven't introduced any nucleophilic aromatic substitution yet, But that is also a reaction that is important for you guys to know. So we've talked about EAS, but we haven't really discussed NAS. So what do you guys think that the N would stand for here? So nucleophilic aromatic substitution. Right, so the name, let the name help you to remember what is going on here, okay? So we have a nucleophile. So remember I said the first letter is going to be representative of what gets added or substituted onto the benzene ring. So that's a nucleophile. And that means that the aromatic ring must be acting as a what? An electrophile. Okay? So if it's acting as an electrophile, does it prefer to have electron withdrawing groups or electron donating groups if it wants to be more electrophilic? You want to have electron withdrawing groups. Okay? That would allow this reaction to proceed. It would increase the reactivity of the benzene rings. So in this case, for NAS, an electron withdrawing group would actually be considered an activator. So that's why I typically don't use the word activating, deactivating, because it depends upon the context. Okay? So here what we have going on, we have a nucleophile, we have a benzene ring. It has a strong electron withdrawing group, so that's good. Let me highlight that for us. Okay, and the bromine is acting as what? It's acting as a good, that will be my hint, a good something. So it's acting as a good leaving group. Excuse me. So it's acting as a good leaving group. Therefore, in nucleophilic aromatic substitution, a nucleophile is going to come and replace something on that ring. But as opposed to how it is in electrophilic aromatic substitution, what it replaces, right, is going to be the leaving group. Okay? So we're in the reaction section. We have our nucleophile, we have our electron withdrawing group, and it makes a difference as to where the electron withdrawing group is. Okay, so NAS, go look at the other video that I made. I think it would really clear it up if any of this is confusing to you, because it really helps to have that conceptual understanding before doing the problems, especially for NAS. But your electron withdrawing group, you have two different mechanisms for NAS. What are the two different mechanisms for anybody that's actually watching this at the live time that I'm going to post it? You have addition, elimination, and then you have elimination, addition. Oops. So the end result is pretty much the same, not quite the same, but in terms of the general gist of it, you are replacing a leaving group with a nucleophile. However, the mechanism at which that occurs is what's different between those. So you have two different routes that this can happen, right? And I like to call addition elimination, I like to call that the Bay route. The Bay route. Bay, like that. Because that is preferred. Okay, so if you have strong electron withdrawing groups on your aromatic ring, right, that helps in order to allow it to occur, the NAS to occur via the addition elimination route. If you do not have them, if you do not have those electron withdrawing groups, a strong one, either ortho or para, they have to be ortho or para, meta doesn't count, then it will undergo the elimination addition route, okay? And that's just a difference in the mechanism at which it takes, okay? They're just flopped, pretty much. So here we are taking the addition elimination route, and the conditions for that you're going to see. It's going to be like you'll have your nucleophile, then you'll have high heat, typically 100 degrees, not 340. That's more for the elimination addition degrees, and of course Celsius. And the elimination addition, this is very harsh. It's a very harsh way to do this. You're forming this benzene intermediate, which is like really wild to have that triple bond within a 6-membered ring like that. That is wild. So that's very harsh to the point that you have to have this at 2,500 psi, high pressure, in order for that to occur. So that's why that's not the Bay route. Okay? And hopefully that's like a little trick to help you to remember that. And what we get is we replace the leaving group, the bromine, we replace it with our nucleophile. And, this is written as only one equivalent. You'll see sometimes with NES reactions, you're going to see 2 equivalents written there. And I explained that in my other video, okay? Or even you can ask about it if you have questions about when it's going to be 1 equivalent versus 2 equivalent, okay? So now let's move on to number 3. So I kind of put a lot of stuff here. Just to prevent us from getting confused, I'll put in black straight away 3. So we have a sodium metal, and we have liquid ammonia, and we have ethanol. Okay, so with this right here, this is called the Birch reduction. This is called the Birch reduction. And like the name is telling, Birch reduction. Reduction, what is reduction? Reduction is the increase of the number of bonds to hydrogen or the decrease of the number of bonds to oxygen. Okay, so in this reaction, what we're doing is we're increasing the number of bonds to hydrogen at 2 specific carbons in the benzene ring. So in the benzene ring, we have these three double bonds, right? Well, now we're going to reduce this molecule so that we only have 2 double bonds in the ring, okay? So that's the general idea of Birch reduction. So I'll put the ring that we had, where we basically had this electron withdrawing group at the para. Oopsies. So we have that basically, and we still have this electron donating group, and then we have the benzene ring, right? So we're trying to arrange double bonds. Basically, with the Birch reduction, you go from this. I'll show you the general idea of it to this. Okay, so you're reducing 2 of the carbons. Which ones are you reducing? That one and that one. And it's always the carbons that are going to be completely opposite the other, right? So you're not going to reduce like that one and the one in the meta position or the one in the ortho. You always are going to be this one to the one way across the way, and it's going to be in the para position to it. Okay, these are the ones that get reduced. So you're basically increasing, if here you have 1 hydrogen, right? Now we're reducing it, so we're increasing the number of bonds to that hydrogen, as well as this side too, right? But I'm just not going to show it because of space, but you have an extra bond to hydrogen in comparison to what you had here, and the same thing happens with the top. Okay, so hopefully it makes sense that we're reducing, this aromatic ring. And if we're reducing it, let's kind of think about this from a conceptual standpoint. So if we're reducing it, we are either we're adding hydrogens, and then another way you could think of this is, remember in Gen Chem, you would think of it as adding electrons, right? So you're adding electrons, and what charge are electrons? They're negative, right? So negative charge. So you're adding something with negative charge, and so that intermediate, you know, that intermediate is going to have a more negative charge in it, right? So things like to be neutral, right? It's more stable to have something neutral than to have something with a full-on negative charge. So having substituents on the ring, right? Particular substituents can help when undergoing this reaction, okay? So if your intermediate is negative, but you want it to be neutral, right? You want to have electron withdrawing groups. Electron withdrawing groups are going to help with this mechanism, because electron withdrawing groups, like the name tells you, they withdraw that electron density that is happening when this molecule is getting reduced. Like that is that the electrons that are getting added, right, that have that negative charge in the intermediate, those can get pulled on those can get pulled on by the electron withdrawing group. So you're stabilizing the intermediate. So my whole point in telling you guys this is that you care about where the electron withdrawing groups are on the molecule. So we're looking over here and we're trying to decide where we want to place our double bonds, right? Because we're going to have two. Which way should we put them? Should we put one here and one here? Should we put one here and one here, or one here and one here? We have to make that decision. And what you praise, what you care about, what is the most important is the electron withdrawing group. Okay, so what is our electron withdrawing group on this molecule? Is it the top one or the bottom one? So your answer should be that it's the bottom one, right? So that is going to be our highest priority, and we're going to praise that, and that's going to be the carbon. Ignore the rest. I mean, you have a donating group. That's unfortunate that we're going to have to reduce the one with the electron donating group. But what we care about the most is the electron withdrawing group. So we are going to reduce the carbon that has the electron withdrawing group. Because, not by. And then the one across from it also gets reduced. So you could draw the hydrogen, but you really do not have to. So that means these are the ones that stay with double bonds. Okay? And, you know, I kind of took a tangent there to explain for those that really care about, like, the conceptual understanding of it and such. But if you're just trying to, you know, get as many points as you can on the test, right? A cute way to remember this, I'd say, remember I said we're praising the electron withdrawing group. So you can pretend that these little lines are your hands, right? So your hands are going to be praising like up and down. And I wish I could show you guys this. I would if we were in person. But they're going to be praising wherever that electron withdrawing group is attached. So that's just a little visual to help you to remember that the lines are going to be, you know, kind of facing it, just like my arms are facing it here, right? Because they praise the electron withdrawing group. Cute way to remember it. Also, another way to remember it is in terms of like hybridization. So if you take the W in EWG and you, let's paste it, and you turn it like that, what number do you get? The W. You get 3, right? So 3, that's a way to help you remember that you want the electron withdrawing group to be on the sp3 hybridized carbon. So this one right here is the one that gains the hydrogen, making it sp3, and you can use the W sideways to help you remember that that is the one that becomes sp3, and then here we couldn't really do much to make this sp2, right? But you really want to have those, if you had the option to make the electron donating group on an sp2 carbon, that would be even better. Electron donating for dos, sp2, and but here, you know, you make your priority the electron withdrawing group. If you have to satisfy one guy, right, you can't please everybody, right? That's the saying. You can't please everybody. So if you have to please only one person, you care about the electron withdrawing group more, okay, than you do the donating group. So that's your answer for that one. Now let's move forward to 5. And we have, right here, we have this weird looking molecule. All right, this dithiane, which she hasn't talked about yet, but we're going to have to talk about it now. And this is a interesting way to add carbon-carbon bonds as well as make aldehydes or ketones, you know, depending on what you prefer to make. So here we see, which one do we see? We see an aldehyde, you know, and a carbon chain attached. So what you want to relate here is this carbon to this carbon, okay? And, you know, if you guys were to definitely take this exam too, you're going to see this on the exam. This is a very, very, very high yield question, you know, where it's like a retrosynthesis. So you practice it a couple times, and I really don't think that is too bad. It looks a lot daunting than what it is. But you basically have these acidic protons. You have these acidic protons, you know, because they're attached at these carbons that are this carbon that's next to sulfur. And if you use a strong enough base, very strong base, you know, there's one that you'll see it written as bully, like a bully. So this is an organolithium reagent where you have a butyl group attached to a lithium. Okay, that's what the Bu is. 1, 2, 3, 4. Okay, so it's a bully, and this is a very strong base, incredibly strong base. And just like a bully, you know, is gonna steal someone's lunch money. This is stupid, but this is a way to remember it. You know, just like a bully would steal your lunch money, this bully here is gonna steal your proton. Right? So it abstracts the proton off of here and puts the electron density onto that carbon. Okay? And you create a carbocation when you do that. So let me put everything else the same. This kind of reminds me of like the head of a virus. It kind of looks like that. Too soon. Too soon, too soon. Gosh, this is crazy. I hope everyone's staying safe and healthy, okay? That's the most important thing. So we form a carbanion, right? And that's after step 1. Now, when you form a carbanion, right, you have a full-on minus charge on a carbon. And that is very unstable, you guys. That definitely wanted to go and react with something. That's like, remember when we did the strong nucleophiles, we had corn nuts from that mnemonic. Bro, I really suck corn nuts. So we had that. And so that's a C with a minus charge. Your Grignard is almost like a C with a minus charge. Same idea here. So that's going to react with your alkyl halides. Okay, so if you're trying to create, so this carbon is adjacent to that carbon there. So you're trying to add this entire group onto that carbon with the carbonyl carbon right here. Trying to add that. So what you want to do is you want to create the alkyl part to that. So if it's just going to mimic it. You're going to mimic the number of carbons, and then you're going to put a leaving group. Just like that. Because what you're going to have here is you're going to have an SN2 reaction where this is going to come. I don't want to draw too much, so I'm going to use the cold laser pointer. This lone pair going to come all in one step, attack right there, push off the bromine. You see that? So when that happens, what are you going to form? You got to draw that out. So, well. So after 2, what we're going to get, you draw the same thing. I'm going to try to paste it, but it's not really working for me. Okay, I'll just draw it like I normally do. So you have the attachment of that group like right here. Like that. You guys see that? So we formed a carbon-to-carbon bond, which is really convenient. And then we have that hydrogen here. And that's corresponding to that hydrogen there. So now we somehow want to get to this like bulbous structure, this circular type thing, 6-membered ring, to this. And what we can do is we can hydrolyze that structure. Oopsies. To get rid of it. This right here. So whenever I say hydrolyze, that should hint to you that we're using water, okay? And we're using water under acidic conditions, so there's going to be some hydronium ion. We also use HgCl2. Okay? The role at which, of which HgCl2, of which it plays, I would not be able to tell you. I do not know that, but you are going to hydrolyze these off, these sulfurs. Hydrolyze them off, and of course, if it's hydrolyzing, you're adding some water, so that's where your oxygen is going to come from. So that's what happens at this step number 3. Right? And you can basically think of it as you're just like taking this off. Taking off the hat, making it goes into a carbonyl. Okay? Let me know if you have questions about that retrosynthesis. If you're trying to make a ketone, you got to do the process twice, okay? Now we have this benzaldehyde over here. And we have Br2, FeBr3. So what type of reaction is occurring here? It's going to be EAS. And what is our electrophile? Going to be Br. And the FeBr3 is acting as what? Your Lewis acid catalyst. Right, and I told you, you're going to see these EAS reactions typically with a catalyst because you got to put something in there in order to create a very strong electrophile, you know. And on our benzene ring, we got to make the decision of where that's going to go and attach. And right here, we have, is this electron withdrawing or donating? So your answer should be that this is an electron withdrawing group. So how is it going to direct? Ortho or para or meta? So it's definitely going to direct meta. I hope my screen's not going to be flipped sideways. But let's just add it, meta. So, of course, there's two meta positions, right? You can use the M to remind you that it's middle, right? It's like in the middle between ortho and para. And it's a bromine that we're adding. So that's going to go right there. And then we go to step number 2. So we have this cyanide. And we have H+, right? So there's some non-aqueous acid. And that's going to just help catalyze this reaction. So you're going to have, you know, this gets activated, this carbonyl carbon here gets activated by the H+. And then you have this come and attack, boom. And then this comes on to the pi electrons come onto the oxygen to give you OH, because you would have protonated it earlier. So you're just having the attachment, the addition rather is a better term, of the cyanide. Oops, and this should be in the meta position. That's my bad. There's UO-, so this is addition. Right? You're adding, and so it gives you 4 single bonds. Right? Okay. So that's what you're going to get in terms of number 6. And for the reaction section, I'm going to just lock this because I'm nervous that it's going to flip on me. But for some reason, my mechanism and synthesis are in the wrong order. I think it's because I was teaching somebody. So let's put the mechanism earlier. Oops, and it looks like I did it for somebody. Okay. So I'm going to break for like a couple seconds, get a drink of water, allow you guys to ask questions. Okay, so I want to do the mechanism now. I really hope that this is going to be in the correct orientation for you guys. So mechanism, let's see. Provide a clear mechanism to explain the formation of the product and use curved arrows to indicate electron flow. Show all intermediates and all formal charges. When more than one resonance contributor may be drawn, be sure to show the most stable contributor. So you'll see a little difference in terms of the instructions from how it used to be like for the first exam as well as in Orca 1, that there's now the addition of this part that says, when more than one can be drawn, you need to show the most stable one. So even if it's not the one that you're using particularly in your mechanism and showing the arrow pushing for, you still have to draw the double-headed arrows like that and put the two resonance contributors, and then let's say the right one is more stable, you put the arrow, an arrow pointing to it, and you can say, like I would write, more stable or most stable, contributor. Okay, so that's what I used to do to ensure that I can get as many points as possible. So let's get started on this. Now, looking at what we have, okay, I like to always look at our reactant here, our reagent, as well as the product. And in terms of the reactant to product, I like to notice any differences between the two. So just list out if you guys have any differences that you notice. I'm definitely noticing that there has been a formation of a ring. So I see a ring formation. So at some point that's going to have to happen. So I'm going to put ring formation. And then in addition to that, I see that we have one OH here, one OH here. So that looks the same between the two, the starting and the final product. But what's different between them is that here you have an OH versus on the other molecule, you do not have that. So you have a loss of water, right? So we'll say loss of H2O. This is kind of like our game plan of what's going on here. And then I also see two methyl, like I see these groups here. Because I know that no CH3 groups can be introduced somewhere else, right? So I also see 1, 2, and 3. So that gives me some insight that something is going to happen there. Probably going to be a methyl shift, but we'll see later on once we, form our carbocation and see what type of alkyl shift that we can do, all right? Then I want to take note of my conditions. So I want to ask myself or ask you guys, is this... would you say this is acidic or basic conditions? So definitely acidic conditions. You have HCl, which is a strong acid. And then we can get started. We can get started from there now that we have a game plan sort of written down. So what do you guys think is the first thing that happen? Identify my nucleophiles. Here, the benzene is a relatively weak nucleophile. It is a phenol, but nothing is happening to our benzene. So let's keep it simple on ourselves, right? We're going to want to protonate this. Right, so I'm going to protonate it first. And I like to keep, you got to keep those benzene ring double bonds, keep them consistent. This is an instance where you don't want to put the circle, the ring, to indicate those pi electrons. In reaction section, that would be perfectly okay, though. Okay, so you protonate it, you form water as a good leaving group. So what do you guys think is going to happen? So water is going to leave. We're trying to get down to a carbocation, because that's when we can have rearrangements happen. You know, that's a good electrophile. So you see there's a formation of a ring. So that's why we want to create that positive charge there. Okay, so what we see going on here, if we're comparing from what we have to our product at the current moment, so we see that there is a formation of a ring, and the ring is getting formed right between these two carbons, right? It's connected over here, and you can see that up here, right? So how many atoms, or how many carbons specifically, are in that ring that we're forming? So we're forming a 6-membered ring, right? So we already know it's going to include 1, 2, and then we need to count our way down the line, right? 3, 4, 5, right? So if we were to try to create, you know, a ring right here, it would be of 5 carbons, right? But really, we want it to be 6 carbons, like up here. So that lets us know, that's our clue, that we have to displace that positive charge to somewhere else on the molecule in order to give ourselves the possibility of creating a 6-membered ring like we have up there. So in order to do that, we can do a shift of some sort. So we could do an alkyl shift, or we could do a hydride shift. However, when we're trying to make the decision, let's look a little bit further, you know, on our product. So remember what I was kind of saying earlier with these 3 groups over here. So I see that there's 2 alkyl groups coming off from here, and then the next carbon over has 1. So that's the little hint, I would say, that lets us know that we want to move this group to somewhere else, right? And if we do that now, then we can get the positive charge over here, and that would allow us to create the 6-membered ring. So that's why I'm going to do that, and we'll try it and see what we get once we move forward. So we're going to do what's called a alkyl shift. I'll write a methyl shift. Should be more exact. Okay, so that's going to move. Oop, and I don't forget your OH like I did. So let me make sure I have that. Yep. Okay, so then we got that. And draw everything else consistent. This one now is going to have that methyl group, and which carbon is going to have the positive charge? It's going to be this one or the right one. So it's definitely going to be the right one now. So I'm going to put it right over here. Oops, this is being really weird right now. I think it's because the pen is not screwed on enough. Okay, so we have a positive charge over there now. So if that were to be the case, now let's count down our carbons, okay? So if we go back, and I can write these in a different colored font. So remember, we're trying to get it to be 6. So 1, 2, 3, 4, 5, 6. Perfect. That's gonna be 1, 2. And we'll see about the numbering for the rest of it. So what we're gonna want to do, this is gonna be an EAS reaction where you have an electrophile, which happens to be this alkyl branch coming off carbocation, and your benzene is going to act as a nucleophile. Remember that. So it's going to go to the ortho position to that alkyl group, and also the para position to that hydroxy group. So you just try to match to your product, right? Doesn't matter. You're trying to make that product and show the arrow pushing for that product. So don't get you caught up in the para and the ortho and all of that stuff. Okay? This, of course, is going to come and attack that number 6 carbon. Okay? And when it does so, you're going to form a 6-membered ring. So I'm just going to, with the phenol, I'm just going to put the double bonds, you know, like that. like that and stuff. And then of course that upper double bond is the one that's breaking, the pi bond right here. That's the one that's breaking and going and gaining this whole group, attacking the positive charge. So if this is the carbon that gets the group, okay, which carbon is going to gain the positive charge? The left one or the right one? I'm going to let you guys, give you guys some time to answer for those that are here, just because this is really important. So the positive charge is definitely going to go to the one on the right, because that's the carbon that is losing the electron in the pi bond, and the other carbon is using that pi bond to go and basically form a now sigma bond to that positively charged carbon. So that is where your 6-membered ring is going to come about. So I wish I drew this a little bit nicer. I'm gonna draw it a little bit nicer for you guys, just to make it look a little bit more like our product in a sense, in terms of the orientation and such. So we got that, then we have the positive charge, and now we're gonna have the group coming off. So we form a 6-membered ring, right? We form it, well, this looks so bad, I'm sorry. Let me draw it better for you. Okay, so we form this 6-membered ring. The left carbon is the one that gained that electrophile, you could call it. And does the carbon on the right, this one, did this have a hydrogen to begin with? Yes or no? So it didn't, but the other one did, right? The number 1 carbon did. And so that's the one that's going to have the hydrogen. Eventually, we're going to have to deprotonate that and reform the aromaticity of the ring, okay? So now the number 1 carbon is attached to which carbon? So this is where you can use your numbering, and it's going to help you out. So 2 is still connected to 3, which is still connected to 4. And we said number 1, what do you guys think? Number 1 is now connected to which carbon? 6. And 6 is still connected to 5. And 5 still has a methyl group on there. And 6 has 2 methyl groups on there. Okay. And now our positive charge is displaced onto the number 2 carbon. So hopefully you guys are starting to see how this lines up with our product. It's starting to line up with our product, right? So what is the difference between our product and what we have right now? So you should be saying something about what we have right now is not, we have not regained the aromaticity of what we have that we see in our final product, okay? Now, this is where we have to pay attention to our highlighted rule that says when more than one resonance contributor may be drawn, be sure to draw the most stable contributor, right? Even if we are not using that most stable contributor in terms of our mechanism, okay? So when we form this over here, right, we have a positive charge on a carbon. Can we draw some resonance to displace that positive charge somewhere else? Your answer should be yes. You can do that. So how can we do the resonance? This will come up and displace the positive charge to that other carbon. Now, if you want to show this all, at the same time to get it to the most stable resonance contributor, that is totally okay. So like that would come down, push this over here. And now we're displacing the positive charge to which atom? Let's draw everything else as it was up there. So I hope you guys see how the rest of it is consistent. You know, I can also put the hydrogen just, you know, because you do not have to though. We also need to have these double-headed arrows, these like this. So hopefully you guys thought that the atom that now has the positive charge is going to be the oxygen. Okay, so that's the whole point of showing the resonance contributors, to show that your oxygen is now the atom that is holding or bearing that positive charge. Because now if we compare between this upper resonance contributor and the lower one, which one is more stable? Which one is a more stable contributor? Thus, which one contributes more to the hybrid? So your answer should be the bottom one. And this is for 2 points. So this is your most stable contributor. You would write it like that, for example. And the reason for that is because all the atoms in this molecule are fulfilling the octet rule. Okay, where they have 8 electrons in their outermost shell, versus whenever you have a carbocation, you are not fulfilling the octet rule. So displace that positive charge onto another atom other than carbon, okay? And you should be good to go. Now, you can use any of the contributors in order to continue in terms of the mechanism. But what I like to use is this one. I think this one is going to be the easiest one for us to see how to continue. And remember, we said the only difference is the formation of the aromaticity, the reformation of the aromaticity of the ring. And in order to do that, we can use a conjugate base, or we could use the water that we formed, actually, because water left as a leaving group. So we can use either of the two of those. So let's see, for example, let's just do it with Cl minus, just because. And the Cl minus can act as a weak base. Remember, because HCl is a strong acid. So conjugate base is weak. And this can come and deprotonate that hydrogen and push the electrons down. And that would get rid of that positive charge, form the double bond, aka reform the aromaticity in our ring and get us up there to our product. So you could use Cl minus or H2O, just like that. If you were to have dealt with the other contributor, you would have to deprotonate this right here. This comes down, this comes here, and this goes on to the oxygen. I think it's best to work with this one here, okay? You will not get any points off for doing that. A lot easier to show as well. Okay. So that is how you do the mechanism. If you have any questions, let me know. I don't know if the exams do go online. No idea how mechanism would be able to be online, unless if the exams get scanned. But we will deal with that on another day when we get there, okay? So I'm gonna move forward to synthesis. Give you guys a couple of seconds to ask some questions. Okay, so let's check out to see what are our starting materials, what we can use for this synthesis, what we're trying to get back to. Okay, I just feel like changing the color because the red is annoying me, so let's go to purple. So our starting materials can be, list out benzene. It also says alcohols of 3 carbons or less. So we're going to go 1, 2, 3 with an OH. Right? And it specifically says alcohol. So I'm not going to put, alkenes or alkenes and alkynes. Okay? And it does actually say here that the stereochemistry of the alkene can be ignored, which is actually very useful and nice of her to do that. Okay, so when we're doing synthesis, what you want to pay attention to is you want to pay attention to the functional groups that you have, and especially on those benzenes, the particular groups you have there, you want to pay attention to their relationship to one another. Like, for example, like if we're looking at the particular one we have here, we're looking at the nitro group, we're looking at this alkene with the other benzene and the NO2 coming off. So in relation between these two, what is their relationship to one another? So you should be saying para, right? So knowing that is going to make a difference in how you act. And then also from here to here, what is their relationship? It's also para. So knowing their, what position they are relative to each other is going to help you out. And you have to pay close attention to that because you have to add these substituents onto the benzene ring. Using EAS, for example, you got to add them in a particular order in order for them to become para, right? Or orthopara. You can't do it so that, like if you have a meta director, you got to be really careful, about doing that, okay? So whenever you have nitro groups need to spark some type of alarm in your head. And the reason why that is because with nitro groups, there's a couple problems. They're sensitive. So there's a couple of problems with nitro groups. Like firstly, a nitro group has a full-on positive charge that's not being shown, on that nitrogen. So you got to be careful in terms of doing a Grignard reaction, using a Grignard reagent in the presence of a nitro group, because the Grignard is just going to react with the nitro group. Remember that from the fact section in the past. So, no Grignard. For some reason, I feel like it looks like I'm spelling Grignard wrong, but I don't know if I am or not, but I'll just put, for example, just in case, I'll put this. Okay, so no Grignard reagent. In the presence of a nitro. Okay, it's going to react. It's going to ruin your Grignard. You're not going to get the designated product that you want to get. Another thing about the nitros is nitro groups are very strong. Are they electron donating or electron withdrawing? So there are very strong electron withdrawing groups. So the issue with having very strong electron withdrawing groups is just for EAS, right? You can't have EAS with a very strong electron withdrawing group on your benzene ring because your benzene wants to act as a nucleophile. And so if you have electron withdrawing groups on the benzene ring, then you are withdrawing electron density from something that wants to have more electron density and wants to just act more nucleophilic. So you want to avoid having those nitro groups. So my suggestion or advice would be to, if you can add those nitro groups as your first arrow, aka as your last step, for sure do it. You know, like here what we see is we see a nitro group that is para to a group that would be ortho-para directing, right? And you also see another one down here, right? So that is just really convenient for you, hopefully, that you can add the nitro group as your last step in the process. So what do you use in order to add a nitro group via an EAS reaction? What should be your reagent on the arrow? Hopefully you're thinking of the nitration mixture, HNO3, H2SO4, and then what you're gonna wanna do, right, we have 2 nitros, so you're adding it to 2 benzene rings, so if you wanna be incredibly accurate here, you can put 2 equivalents. Whether or not you're gonna get points off, I'm not sure. I don't think that you would, honestly, but I would personally put 2 equivalents, okay, or even excess, but rather 2 equivalents, okay? Now, I want to draw everything else the same. I'm going to draw everything else just like that. Like this, like that, like that. Whoops, we're not supposed to have these nitrate groups, so I'm going to remove them. And then we also have another. So is this really a symmetrical molecule? Yeah, it looks like it is. So it's a symmetrical molecule, exactly. Interesting choice. Okay. So now our functional group. So just to cover that a little bit more, you added the nitration mixture, you added it into equivalents, so it adds to both the benzenes, and then this group over here is definitely going to be ortho-para directing, right? Because it's an alkyl chain, no oxygens, nothing, right? So it's ortho-para directing to both of these, and that doesn't really matter. You know, in terms of the mixture there, she's assuming that you've isolated the para product, and in fact, that's pretty, I mean, there's some steric hindrance involved. So your major product would probably be the para product, okay? But don't worry too much about that, okay? Now, yeah, like you could literally, if you're super, you know, perfectionist, you want to be sure, you can put isolated para. Okay. Now you identify your functional groups that are present in this molecule. So you have these benzenes and you also have the double bond, right? So this is where my suggestion would be, if you can deal with a double bond, deal with the double bond. So you want to ask yourself, what is a way at which I could create a double bond, right? And what should I have had on my molecule before that in order to do so? Okay, so she said in the instructions, which is very interesting, she said that the stereochemistry of the alkene may be ignored. So that's really awesome. You know, that's helpful because now you don't have to particularly either do a Witting reaction. You don't have to do, there's one other reaction. Yeah, you don't have to do reduction of a alkyne to get the alkene. You know, with the dissolving a metal route, you don't have to do that. You can go with plain old H2SO4 with heat. And what's so awesome about that is that you can get back to an alcohol, right? You can get back to having an OH group on there. So I'm just going to draw everything kind of as is, right? I'll put the CH3 or CH2, CH3. I'll put the benzene ring like that. And then we have the other carbon that's a part of the double bond. And then we also have this. So same thing on the other side. And then we have to make the decision of putting the alcohol there, right? I mean, it doesn't really matter for this one because you have a symmetrical molecule. So it doesn't matter if you put it on the right carbon versus you put it right carbon versus putting it on the left carbon. Okay. So if we were to put it there, we ask ourselves, hypothetically speaking, where would we get the double bond? And it would go right here in between the OH and the H, because it cannot go here, right? Because you have the benzene ring. So if you drew out the bonds for that, that would help you to see that. Oops. You know, hopefully that helps you out to see why you could not put the double bond right here. You see, because there's not a hydrogen here, right? This carbon has 4 bonds to carbons. Okay, so it's definitely going to force it to form, you know, right in the middle there. I feel like my thing is lagging a little bit. So I'm going to go like that just to restart it. Yeah, that's better. Okay. So now that we got back to our alcohol, what's perfect about an alcohol and why I like that H2SO4 and He method is because you can get back to doing a Grignard, right? Alcohol is like amazing in terms of synthesis. So we can go back to doing a Grignard. And of course, for a Grignard, you're going to have 2 components. And you're also going to have the NH3 plus on our arrow, but we will add that later. So we're going to break this up. And we're going to make one piece the Grignard reagent, and we're going to make the other piece a carbonyl of some sort. Okay, I like to make the bigger piece my Grignard. I noticed that you have less steps later on. That is up to personal preference of how you want to do this. I would do it like this. I would make my right piece my Grignard. Okay, so I'll put this, okay, attach it to the carbon that has a hydrogen and also has a CH2, CH3, and put an MgBr. So that is our strong nucleophilic Grignard reagent. And then we're also going to have the other piece, right? So we have a big benzene with a carbonyl carbon, and that's going to have the CH2, CH3. And in terms of mechanism between this, what we're going to have is a nucleophile coming and attacking right here. Pi electron becoming a lone pair. So what do we have to put on our arrow? Then H3O plus. So I always go back and check my Grignard mechanism. Always, always, even until this very day. I always do it to never forget that and make sure that I'm connecting this in the proper manner and not missing any carbon, not at all. Right, so this bond forms directly to the carbonyl. Now it's up to you which side you want to deal with first. Let's just deal with the Grignard side because I think a lot of you guys know how to make a Grignard. So what are you going to have to put on your arrow? So you're definitely going to put Mg and ether. Hopefully you got that. And then we have this benzylic position, right? That's a 1 over from the benzene ring of the double bond right here. And we have a bromine there. So when we have that, what we want to do is use a reagent that particularly, you know, it's very selective to add a bromine at that benzylic position, You have two options for this, but I like to just do NBS. And of course, you got to include the fact that you have light. So I put that, and that would have replaced a hydrogen on that carbon. So you have everything else the same, except it's a hydrogen as opposed to the bromine. What else could you have put there that works? Because it would give you the benzylic position with a bromine as your major. You could also do Br2 and light. That's what you could also do. Now, we're trying to get back to, my goodness, we're trying to get back to a benzene, alcohol, 3 carbons or less. So there's still some parts of this left. So how can we get a CH2? We basically have a propyl group on our benzene ring. We have a propyl group. So if we had, let's say we had this before with 3 carbons, carbonyl, carbon, you want to avoid alkylation. Friedel-Crafts alkylation, you want to avoid it, right? So the best way for your synthesis is to use Friedel-Crafts acylation. Avoid Friedel-Crafts alkylation. There are too many problems with that. You have the possibility of polyalkylation, which is where you add alkyl groups all around the ring. You can't stop it because the benzene is getting so activated, right? You also have a problem with branching. You'll get rearrangements of the carbocation intermediate that you form, okay? So you want to definitely get back to Friedel-Crafts acylation. So if you were to have what I put over here like this, and you're trying to go to this, right? The only difference between this and this is that we reduce this carbonyl carbon. And in order to do that, what reagent do we have to use? In aqueous HCl. So I would personally put aqueous, and that would reduce that carbonyl carbon all the way to a CH2. So a cute way that I tell people to remember this is that you're zinc the head off the carbonyl. So you're zinking the head off the carbonyl, you're making it a CH2 right here in its replacement, and that's how you get that. So what's another name for that type of reduction? So you should be saying Clemenson. And Clemenson is in acidic conditions, okay? So that might be something to watch out for a little bit later in the course, okay? Now, here, what we have is we had Friedel-Crafts acylation, right? So we added an acyl group, which is just this, onto our benzene ring. So, of course, we would have started off with the benzene like this, and that's what we're trying to get back to, which is awesome. And then we have an acyl chloride, like this, right? And so we're trying to do Friedel-Crafts acylation. So what am I forgetting to put on my arrow? What do I have to add to my arrow? Our Lewis acid catalyst, AlCl3. Okay, so this is an EAS reaction. This is a type of EAS reaction. And we got back to our benzene, but now we want to get back to alcohol, 3 carbons or less. So this has 3 carbons. But what can we do as our previous step to get it back to an alcohol, right? So whenever you see the acid chloride, there is one reagent that you want to use, right? And why you want to use it is you can form the acyl chloride by replacing hydroxy of a carboxylic acid with a better leaving group, which is chlorine, okay? So we go back to a carboxylic acid, and remember, we're trying to get back to an alcohol. So we're 3. Trying to get back to an alcohol, so let's just put that down. 3 carbons like this. So we basically did an oxidation process, an oxidation step in order to oxidize it all the way to the carboxylic acid. So there are some reagents that you could do in order to do this. What do you guys think? All the way to a carboxylic acid has to be relatively strong. So you can put Jones ox. Another option is sodium dichromate. So 2O7. I think I used to remember this as like 007 or something like that. So I used to remember it. H2SO4, of course, and then you're gonna be dilute, right? So this is different than what happens when you have oxidative cleavage of a benzene ring substituent. Okay, this is sodium dichromate here is responsible for oxidizing a primary alcohol all the way to a carboxylic acid, right? Or a secondary alcohol to a ketone. And same thing as Jones ox. They do the same thing. They do the exact same thing. Okay, so that's how you get back to a propanol. And that looks good. And now I really recommend when you guys are doing this, like go back and read the entire thing from here all the way up, you know, and do that on your exam when you're taking your exam. So for the other piece over here, this other piece is the same exact thing. When I say this other piece, I mean this right here. That is the exact same thing as this, which we already formed all the way over here. So for this, I would just write this asterisk saying already synthesized, right? You don't have to repeat and be redundant and write the same thing again, okay? Okay, so that's how I would personally do the synthesis. You could have used Whitting reaction if you know how to make that Yllid. Actually, no, I think you would still get 1 point off for that, because to create the Yllid, you would have to have this. And that's not allowed. You're not allowed to start with that. You're not allowed to start with it, so yeah, I don't think you could use that to get 100% full credit. But of course, if you remember it, do that, okay? But I would take this route, especially because she's being nice with this stereochemistry thing. Okay. Now, let's look at spectroscopy. So it says a compound with the formula... Wait, actually, I'm going to drink water. A compound with the formula C11H14O exhibits the IR proton NMR and proton decoupled C13 NMR spectra shown below. So please identify this compound and draw the structure in the box provided below. Okay, so let's start off with our IR. And check out what we have. So if we're going to mark this at the fingerprint region, mark it right here, about here. Everything to the right, I'm just going to say that that's our fingerprint region. And then to the left of this, we have something. Well, you know what? I actually jumped the gun. Shame on me. Shame on me. What do we have to do before we even look at the IR? you want to calculate your unsaturation number. So that is my bad. Make sure you do that first, because that really will clear up some things for you, okay? Give you some more clarity. So 2 times carbon. So I want you guys to, you know, solve the formula. Remember the formula. Solve the formula on your own. And oxygens don't make a difference. Remember that. So we're going to do 2 multiplied by the number of carbons. Okay, so hopefully you guys got 5 as well. All right, so whenever we see an unsaturation of 4 or greater, what are we going to have in our molecule? We're going to have a benzene ring somewhere, because that's giving us an unsaturation of 4. And in addition to that, we'll have a double bond of some sort somewhere. Could be a carbon-carbon double bond. Could be a carbon-oxygen double bond. We do have an oxygen here. We have 1. So it could very likely be that, okay? So let's go back to the IR spectrum, see what we have. So we have a 1597.26. So that is going to be most likely. It's not deep. It's almost, you know, I mean, it's almost 1500. So that's going to be your double bonds within your benzene ring. Then let's look to the next part. And this part is kind of hard to see. This absorption band, I don't know if anyone else can read it a little bit better than me, but it looks as though, just based upon the ticks, that it's got to be 1600 something. And then 87 point something. So we'll just put that. Okay, 1687 is what we see. And it's a very deep absorption band. So whenever it's deep like that, that's going to lead me to believe that this is the carbonyl absorption. I'm not going to bet my entire life on it, right? But I'm really leaning in that direction because of the fact that it's further down, right? So it's almost a 1700. You know, I mean, it could be conjugated. You don't know that. We don't know that. But it's just because of how deep it is. That's the reason why I would say that that's probably going to be a carbonyl, you know. But with IR, you know, I never really bet my life on anything because I don't want to go into it so close-minded, right? So I'm just going to take that with a grain of salt and then continue on to my 3000 region. See if there's anything of importance here. Nothing, you know, absence of the alcohol, absence of an aldehyde, anything indicating an aldehyde here, and that would also show up something in our proton NMR. So absence of aldehyde, you know, this also shows some sp3 carbon to hydrogen bonds, which are present in every single, you know, organic molecule pretty much. So nothing distinctive there, okay? But we have established that there's probably a carbonyl that oxygen is going to be involved in, and that would you know, satisfy the fact that we have an unsaturation of 5. So let's move forward to our proton NMR and make our way from right to left and put the things that we, you know, we feel pretty confident about in boxes. So we have an integration of 3. So that lets me know that we have probably a CH3. And of course, a splitting pattern. It's probably next to something. It has to be next to something with 2 protons on it. Okay, so I'll put CH3 like that. It's probably going to be next to a CH2 just because it, you know, it's next to something with 2 protons. But let's continue our way down the line. So we have a CH2, another CH2. Look at how similar their splits look to be. And they have so many splits that it's probably, You know, I mean, there's some overlap here, right? So whenever you see this pattern, this is distinctive of having a chain, like CH2, CH2 chain, because you have all this complex splitting from either side. So this is probably going to be connected to more, you know, CH2 from the other side. And this one here is going to be connected to something else that also has protons from the other side. They're not incredibly downfield. So that would also, you know, fit the fact that they're not next to a carbonyl. They can't be because of the splitting pattern. And then let's look over to the 3.0 region. So how come this thing is so downfield in comparison to the others? There must be a reason as to why that is. And its splitting pattern is 2. So from one side, it should be connected to something that has how many protons? 2. And I should say its splitting pattern is 3, but that tells us that in +1 rule, it tells us that you have 2 protons adjacent. Right? From the other side, you wouldn't have anything. Okay. And it's downfield. So very likely that's going to be connected to the, well, we know that there's probably a carbonyl here, so it's not going to be directly attached to it, like as an ether, but probably to the carbon that has the carbonyl, but we'll check that once we get there. So we come down to like past the 6.5 region. So here it's 7.2 in particular to 8.4, right? And in this region, this is the region for what? This is our aromatic ring region. And our integration number is telling us that we have 5 protons. So if we have 5 protons on this, then what is our substitution of the benzene? How many substituents we have? Like non-hydrogen substituents, obviously. It's mono. So it's mono substituted. That's why we have an integration of 5, because one of those spots is being taken by a group. So that's why that one doesn't show that it has a proton, like right here. Doesn't show that it has a proton. So now that we have all this written down on the paper, what I want us to do, and this is what I really recommend for you to do to make sure you never forget a single carbon. You count the number of carbons you've written on the paper. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10. Does this match our molecular formula? No, it doesn't match our molecular formula. We are missing 1 carbon. That is our clue. That is our clue right there. That it has to be the carbonyl carbon. Right? That we are not accounting for. That satisfies the fact that there's 1 oxygen. Satisfies the number, the 11 carbons. And you can also count the number of hydrogens to make sure that it is 14. Yep, counted it. It is 14. And now we have to just connect these things. So hopefully this one is not too bad, that you can just, you know, this has to be connected to something with 2. CH3 has to be on the end of the molecule, so it goes here. We have this CH2 chain, actually, and there's complex splitting here from both sides because the groups on left and right are different environment. So that CH2 has to be connected to the other one. How come this CH2 is so downfield? Or 3.0, it's not 4.0, so it's not direct, it's not like an ether, but it's connected to the carbon that has the oxygen on it. And there's only one more place for this to be connected, and that's to the benzene ring. And that satisfies that the benzene is mono-substituted. And we actually do have a conjugated benzene ring, right, to the carbonyl carbon. And that would explain why this right here is a little bit less than 1700. Okay, and you don't need, you see how we did that without using the carbon-13? You can use it if it, you know, it makes you feel good that it's, drilling home what you believe. But in terms of, determining symmetry or determining how many different environment carbons you have, you could use that and count it. But in terms of this, it's kind of hard to see if this is 2 or just 1. And also the benzene ring, sometimes there's some issues there in terms of determining different environment carbons when you just haven't like a carbon, a chain coming off of it like that, Hypothetically, this and this should be the same, this and this should be the same, and this should be different from those. Okay, I will put those in different colors for you. Boom, 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 boom. Like that, for example. That's a hypothetical thing. In terms of the protons, as well as those carbons at which those protons are attached. In terms of the carbon-13. So in terms of writing this in the box, CH3, CH2, and I'm going to definitely, check this alongside the key. So far, I've checked everything alongside the key after I do it. So to mention if she says anything about points. Oops, that looks kind of... Okay, let me check it. 1, 2, 3, 4. Yeah, so that looks great. That looks great. So that is your answer. And that is the entire exam from start to finish. I hope that this was helpful. I'm sorry that we couldn't meet in person. But I'm going to go back and leave it here. Oops. Okay. So that is it. Okay, so you can leave a comment, definitely. If you have a question, you can... I prefer you to write in the comments or even in that live chat. Hopefully that works for you as well. I will be there, 7 o'clock. Okay, thank you so much, you guys. And best of luck. Keep studying hard, okay? Keep working hard because I promise you the information is going to be very useful for your final and for your third exam.